Modeling complex time series. The necessity of the ARMA model. In previous sections, we explored autoregressive AR models, which capture the dependency of a current observation on its past values, and moving average MA models, which account for the dependency on past forecast errors. Both AR and MA models describe distinct types of time series behavior, and their respective autocorrelation function, ACF, and partial autocorrelation function, PACF, plots exhibit characteristic patterns, e.g., AR-P. Models have PACF that cuts off after lag code snippet and ACF that tails off. MAQ. Models have ACF that cuts off after lag code snippet and PACF that tails off. However, many real-world time series exhibit characteristics that are a blend of both autoregressive and moving average processes. For instance, economic data, stock prices, or sales figures often show dependencies on both previous values and previous unpredictable shocks or errors. When a time series is influenced by both its own past values and past white noise error terms, neither a pure AR model nor a pure MA model will fully capture its underlying structure. Attempting to fit a pure AR model to a process that also has MA components might require an excessively high AR order to approximate the MA behavior, leading to an overly complex and potentially unstable model. Similarly, fitting a pure MA model to a process with strong Arkansas components would face similar issues. This limitation necessitates the introduction of the Autoregressive Moving Average, ARMA, model, which combines the strengths of both AR and MA components to provide a more parsimonious and accurate representation of complex time series dynamics. The ARMA model allows us to model a wider range of time series patterns that are not adequately described by either pure AR or pure MA models alone. The Autoregressive Moving Average, ARMA, model defined. The Autoregressive Moving Average, ARMA, model, denoted as ARMA, PQ, is a powerful tool for modeling stationary time series data. It combines the code snippet terms from the autoregressive AR component and the code snippet terms from the moving average MA component. Mathematically, an ARMA PQ model can be represented as $YT equals C plus backslash phi 1 Y, 1 plus backslash phi 2 YT2 plus backslash FIP YTP plus backslash epsilon plus backslash theta 1 backslash epsilon, 1 plus backslash theta 2 backslash epsilon 2 plus backslash thetac backslash epsilon TQ, where $YT is the value of the time series at time code snippet. $C is a constant term, intercept. Backslash phi 1 backslash phi 2 backslash FIP are the autoregressive parameters, representing the influence of past values of $YT. $YT on YTP are the past code snippet values of the time series. Backslash epsilon is the white noise error term at time code snippet, assumed to be independently and identically distributed ID, with a mean of 0 and constant variance, backslash sigma caret $2. This term represents the random shock or innovation at time code snippet that is not explained by the model. Backslash theta 1, backslash theta 2, backslash thetac are the moving average parameters, representing the influence of past error terms. Backslash epsilon T1, backslash epsilon T2, backslash epsilon TQ are the passcode snippet white noise error terms. In essence, an ARMA PQ model posits that the current value of a time series, $YT, is a linear combination of its passcode snippet values and its passcode snippet white noise error terms. The AR part, backslash phi 1 Y, 1 plus backslash FIP Y TP captures the memory of the process based on its own history, while the MA part, backslash theta 1 backslash epsilon, 1 plus backslash thetac backslash epsilon $, accounts for the impact of previous unobserved shocks or innovations. This dual mechanism allows the ARMA model to capture more intricate patterns of dependence than either pure AR or pure MA models. Challenges in model identification. ambiguous ACF/PACF plots. For pure AR-P processes, the PACF cuts off sharply after lag code snippet, while the ACF tails off. For pure MAQ processes, the ACF cuts off sharply after lag code snippet, while the PACF tails off. These clear patterns make it relatively straightforward to determine the order's code snippet or code snippet for pure AR or MA models, respectively. However, when a time series is an AR-MA, P, Q process, the situation becomes more complex. The mixing of autoregressive and moving average components causes both the ACF and PACF plots to exhibit more intricate and often ambiguous patterns. Specifically, ACF of an AR-MA process will show a tail ing off pattern, influenced by both the AR and MA components. It will not cut off sharply. The decay might be exponential or sinusoidal, but it will persist. PACF of an AR-MA process will also show a tailing off pattern similarly influenced by both components and will not cut off sharply. Its decay might also be exponential or sinusoidal. This means that for an AR-MA process, neither the ACF nor the PACF will show a clear cutoff point. Instead, both plots will typically display a gradual decay or a more complex, possibly sinusoidal, pattern that extends over many lags. This ambiguity makes it very difficult, if not impossible, to reliably determine the appropriate code snippet and code snippet orders by simply inspecting these plots. Consider a real-world example: daily stock returns. While past returns might directly influence current returns, AR component, unexpected news or market shocks, error terms, from previous days might also have a lingering effect, MA component. When analyzing the ACF and PACF of such a series, you wouldn't see a clean cutoff. Both plots would likely decay slowly, perhaps with some oscillations, making it hard to eyeball the exact code snippet and code snippet values. This inherent ambiguity underscores the need for a more systematic and robust approach to model selection for AR-MA processes. A systematic approach to time series modeling. Given the limitations of ACF and PACF plots for identifying AR-MA orders, a more systematic and rigorous procedure is required. This procedure moves beyond visual inspection and relies on statistical criteria and diagnostic checks to select the best model. The core of this systematic approach involves two critical phases. 1. Model selection, using information criteria to compare and select the best fitting model from a set of candidate models. 2. Model validation, thoroughly examining the residuals of the selected model to ensure it adequately captures the underlying data-generating process and meets the necessary statistical assumptions. This systematic approach is crucial for building robust and reliable forecasting models and forms the foundation for modeling even more complex time series, including non-stationary and seasonal data, which will be discussed in later chapters. Model selection, the Akaika Information Criterion, AIC. When dealing with AR-MA models, we often need to choose the optimal order's code snippet and code snippet from a range of possibilities, e.g., AR-MA 1-1, AR-MA 1-2, AR-MA 2-1, AR-MA 2-2, etc. The Akaika Information Criterion, AIC, is a widely used statistical measure for model selection that helps us navigate this challenge. What is AIC? The Akaika Information Criterion, AIC, is an estimator of the relative quality of statistical models for a given set of data. Given a collection of candidate models for the data, AIC estimates the quality of each model relative to each of the other models. It provides a means for model selection. The primary goal of AIC is to find a model that explains the data well, while also being parsimonious, simple. It strikes a balance between goodness of fit, how well the model fits the observed data. A model with more parameters, higher code snippet or code snippet, will generally fit the training data better. Model complexity, the number of parameters used in the model. More parameters mean a more complex model, which increases the risk of overfitting, where the model performs well on training data, but poorly on new, unseen data. The formula for AIC is generally given by $AIC equals 2K, 2\ln\hat where code snippet is the number of estimated parameters in the model. For an ARMA, PQ model, code snippet for the constant code snippet plus 1 for the variance of the error term. So typically code snippet $hat L is the maximum likelihood estimate of the likelihood function for the model. The likelihood function measures how well the model parameters explain the observed data. How is AIC used for model selection? When comparing different ARMA, PQ models for the same time series, the model with the lowest AIC value is generally preferred. A lower AIC indicates a better balance between model fit and model complexity. The process typically involves 1. Define a search space. Choose a reasonable range for code snippet and code snippet, e.g., code snippet from 0 to 3, code snippet from 0 to 3. 2. Fit candidate models. For each combination of code snippet within the search space, fit an ARMA, PQ model to the data. 3. Calculate AIC. Compute the AIC value for each fitted model. 4. Select the best model. The model with the minimum AIC value is chosen as the preferred model. Common pitfall: relying solely on measures of fit like R-squared or mean squared error, MSE, can be misleading. A more complex model, higher code snippet or code snippet, will almost always yield a better R-squared on the training data. AIC penalizes model complexity, thus encouraging the selection of the simplest model that adequately explains the data, helping to mitigate the risk of overfitting. Model validation, residual analysis. Once a candidate model, e.g., an ARMA, PQ model with optimal code snippet and code snippet determined by AIC, has been selected, it is crucial to validate its appropriateness. Model validation is performed by analyzing the model's residuals. Residuals are the differences between the observed values and the values predicted by the model $epsilon equals YT \hat YT $. For a model to be considered a good fit, its residuals should resemble white noise. This means the residuals should ideally possess the following characteristics. 1. Zero mean. The average of the residuals should be close to 0. This indicates that the model is not systematically over or underpredicting. 2. Constant variance. Homoscedasticity, the spread of the residuals, should be consistent over time, with no discernible patterns of increasing or decreasing variance. Plain. Autocorrelation. The residuals should be independent of each other. There should be no remaining patterns or information that the model failed to capture. If residuals are correlated, it means there's still structure in the data that the model hasn't explained. 4. Normality. Optional but desirable for inference while not strictly required for the model to be valid. Normally distributed residuals are often assumed for statistical inference, e.g., constructing confidence intervals for forecasts. To assess these characteristics, several diagnostic plots are commonly used. 1. Correlogram, ACF plot of residuals. Purpose: to check for any remaining autocorrelation in the residuals. Interpretation: if the model has adequately captured all the time series dynamics, the residuals should be uncorrelated. Therefore, the ACF plot of the residuals should show no significant spikes, i.e., all spikes should fall within the confidence bounds, typically represented by dashed lines. Insight: if significant spikes are present, it indicates that the model is misspecified and there is still predictable information left in the residuals, meaning the model hasn't captured all the underlying patterns. This would necessitate re-evaluating the model orders or considering more complex models. 2. QQ plot, quantile plot. Purpose: to assess whether the residuals are normally distributed. It compares the quantiles of the residuals to the quantiles of a theoretical normal distribution. On interpretation: if the residuals are normally distributed, the points on the QQ plot should fall approximately along a straight diagonal line. Insight: deviation from the straight line, e.g. S-shapes, heavy tails, suggest that the residuals are not normally distributed. While not always a deal breaker for forecasting, non-normality can affect the validity of confidence intervals and hypothesis tests. 3. Density plot. Histogram of residuals with kernel density estimate. Purpose: to visualize the distribution of the residuals. Interpretation: for normally distributed residuals, the density plot should approximate a bell-shaped curve centered around 0. Insight: this plot provides a visual complement to the QQ plot, offering an immediate sense of the shape, symmetry, and spread of the residual distribution. Skewness or multiple peaks would indicate non-normal behavior. In addition to visual inspection, formal statistical tests, e.g., Ljung-Box test for autocorrelation, Jark-Barra test for normality, can be applied to the residuals to provide quantitative evidence for white noise assumptions. The general modeling procedure for complex time series. Building a robust time series model involves a systematic, iterative process. Here is a general procedure, integrating the concepts of AIC for selection and residual analysis for validation. 1. Data preparation and stationarity check. Load and inspect the time series data. Assess for stationarity using visual insp. Action, e.g., run sequence plot, and statistical tests, e.g., augmented Dickey-Fuller ADF test. If non-stationary, apply differencing to achieve stationarity. The concept of differencing and non-stationarity will be covered in detail in subsequent chapters. 2. Initial model identification, exploratory. Examine the ACF and PACF plots of the stationary series. For ARMA processes, these plots will likely be ambiguous, showing tailing off patterns for both. However, they can still provide a starting point or suggest a range for code snippet and code snippet to begin the systematic search. For example, if the PACF drops off quickly after a few lags and the ACF tails off, it might suggest an AR component. If the ACF drops off quickly and the PACF tails off, it might suggest an MA component. For an ARMA, both tail off, so this step becomes less definitive. 3. Model estimation, iterative search. Define a reasonable range of code snippet and code snippet values to explore, e.g., code snippet from 0 to 3, code snippet from 0 to 3. Fit an ARMA, P, Q model for each combination of code snippet within this range. This involves estimating the model parameters $\phi$ and $\theta. 4. Model selection using AIC. For each fitted model, calculate its Akaike information criterion, AIC. Select the model with the minimum AIC value. This model represents the best balance between goodness of fit and model complexity among the candidates. 5. Model validation, residual analysis. Extract the residuals from the selected model. Generate and interpret the diagnostic plots for residuals. Correlogram. ACF of residuals, check for remaining autocorrelation. QQ plot. Check for normality of residuals. Density plot. Visualize the distribution of residuals. Optionally, perform formal statistical tests, e.g., Ljung-Box test, on the residuals to confirm they resemble white noise. If residuals show significant patterns, e.g., strong autocorrelation, the model is likely misspecified. Return to step 3, adjust the search space for code snippet and code snippet, or consider more advanced models. 6. Forecasting. Once a validated ARMA model is obtained, it can be used to generate future forecasts. The model uses its estimated parameters and past observed data and past errors to predict future values of the time series. This systematic procedure provides a robust framework for identifying, estimating, and validating time series models, moving beyond the limitations of visual inspection and laying the groundwork for accurate forecasting. Forecasting bandwidth usage for data centers. Predicting future resource needs is a critical task for any organization managing large-scale infrastructure, and data centers are no exception. Effective forecasting of bandwidth usage allows data center operators to optimize resource allocation, prevent outages due to insufficient capacity, and minimize costs by avoiding over-provisioning. This section demonstrates how time series forecasting methodologies, particularly ARMA, Autoregressive Moving Average, model identification and selection, can be applied to this real-world problem. 1. Data acquisition and initial exploration. The first step in any time series analysis is to obtain the relevant data and perform an initial visual inspection. For this example, we'll simulate bandwidth usage data, as real-world data might contain proprietary information. Our simulated data will exhibit characteristics common to actual bandwidth usage, such as a general trend, some cyclical patterns, e.g., daily or weekly peaks, and inherent noise. To begin, we'll use code snippet for numerical operations and code snippet for handling time series data. We'll also set up code snippet for plotting. Download the code on one patch code Substack. This initial code segment imports necessary libraries and sets up the foundation for our data simulation. We've chosen code snippet hourly data points, which simulates approximately 14 months of continuous bandwidth measurements, a reasonable time frame for OPE. Rational planning. The code snippet function generates a proper time index, which is crucial for time series analysis. Download the code on one patch code Substack. Here, we construct the components of our simulated time series. Code snippet captures the general growth in bandwidth demand. Code snippet and code snippet introduce realistic periodic fluctuations, mimicking usage patterns within a day and across a week. Finally, code snippet is generated with code snippet and will be processed to exhibit ARMA characteristics later, making the data more realistic than simple white noise. Download the code on one patch code Substack. In this final data generation step, we combine all the components. Note that while we initially planned for a full ARMA noise generation, for clarity and to ensure the data effectively demonstrates the ARMA identification process, we've opted for a simpler AR-1 process for the noise component added to the trend and seasonality. This ensures our simulated data will genuinely exhibit autoregressive characteristics, making the subsequent ACF/PACF analysis more illustrative. The generated code snippet is then plotted, providing a visual overview of the data's behavior over time. This plot, figure 6.1, immediately reveals the presence of trend and seasonality, suggesting that the series is non-stationary. 2. Checking for stationarity with the augmented Dickey-Fuller ADF test. Before we can effectively model a time series using ARMA models, it is crucial to ensure that the series is stationary. A stationary time series has statistical properties like mean, variance, and autocorrelation that do not change over time. Many time series models, including ARMA, assume stationarity. Non-stationary series can lead to spurious regressions and unreliable forecasts. Visual inspection from figure 6.1 suggests non-stationarity due to the clear upward trend and periodic patterns. To formally test for stationarity, we use statistical tests like the augmented Dickey-Fuller ADF test. The null hypothesis $H0 of the ADF test is that the time series is non-stationary, i.e., it has a unit root. The alternative hypothesis $H1 is that the time series is stationary. Therefore, if the p-value from the ADF test is less than a chosen significance level, e.g., 0.05, we reject the null hypothesis and conclude that the series is stationary. Download the code on one patch code Substack. This code snippet executes the code snippet function from code snippet on our code snippet. It then neatly prints the ADF statistic, the p-value, and the critical values at different significance levels. The interpretation logic immediately tells us whether the series appears stationary or not based on a standard 0.05 significance level. As expected from our simulated data, with a trend, the p-value will be high, indicating non-stationarity. If a series is found to be non-stationary, it often requires differencing to achieve stationarity. Differencing involves subtracting the previous observation from the current observation, $YT equals YT, $1. This process helps remove trends and seasonality. For our data, which clearly has a trend and seasonality, We will apply first-order differencing and then recheck for stationarity. Download the code on one patch code Substack. Here, we calculate the first difference using the code snippet method and remove the resulting code snippet value with code snippet. We then plot the difference series, figure 6.2. Visually, this series appears much more stationary, fluctuating around a constant mean. A second ADF test confirms its stationarity, indicating that a single differencing operation, i.e., $D equals $1 in an ARMA model, is sufficient. 3. ARMA model identification using ACF and PACF plots. Once stationarity is achieved, the next step is to identify the appropriate orders for the autoregressive, AR, and moving average, MA, components of our model. This is typically done by examining the autocorrelation function, ACF, and partial autocorrelation function, PACF, plots of the stationary series. Autocorrelation function, ACF, measures the correlation between a time series and its lag values. Partial autocorrelation function, PACF, measures the correlation between a time series and its lag values, after removing the effects of intermediate lags. Interpreting ACF and PACF plots for ARMA models can be challenging because both AR and MA components contribute to patterns in both plots. However, some general rules of thumb exist. Por approaches. ACF decays exponentially or sinusoidally. PACF cuts off abruptly after lag code snippet, i.e., significant at lags 1 to code snippet, then non-significant. Por process. ACF cuts off abruptly after lag code snippet. PACF decays exponentially or sinusoidally. Mixed ARMA, PQ process. ACF decays exponentially or sinusoidally, influenced by MA component initially, then AR. PACF decays exponentially or sinusoidally, influenced by AR component initially, then MA. Both plots show a mix of decaying and cutting off patterns, making identification more nuanced. This is where model selection criteria like AIC become crucial. Let's generate the ACF and PACF plots for our difference bandwidth usage data. Download the code on one patch code Substack. This code block uses code snippet and code snippet to generate the correlograms. We specify code snippet to observe patterns over a reasonable range of past observations, and code snippet to display the 95% confidence intervals, the blue shaded region. Any spikes extending beyond these shaded regions are considered statistically significant. Interpreting figures 6.3 and 6.4. ACF, figure 6.3, we observe several significant spikes, followed by a somewhat sinusoidal and slowly decaying pattern. This suggests the presence of both AR and MA components, and possibly remaining seasonality. The significant spikes at specific lags, e.g. 24, 48 for hourly data reflect. ING daily patterns indicate remaining seasonal autocorrelation. PACF, figure 6.4, similar to the ACF. The PACF also shows significant spikes and a decaying pattern, rather than an abrupt cutoff. This further confirms a mixed ARMA process. The seasonal spikes in PACF also indicate seasonal AR components. Given the complexity, especially with the presence of seasonality, which an ARMA model alone doesn't directly handle, but an ARMA DQS model would, and the non-clear cutoffs, relying solely on ACF/PACF, can be ambiguous. This is precisely why model selection criteria become indispensable. 4. ARMA model selection with Aikaika information criterion, AIC. When dealing with mixed ARMA processes, or even when the ACF/PACF plots are not perfectly clear for pure AR/MA processes, a more systematic approach to model selection is required. The Aikaika information criterion, AIC, is a widely used metric for this purpose. AIC provides a means to compare different statistical models. It estimates the relative amount of information lost by a given model, with a lower AIC value indicating a better model. AIC balances the goodness of fit of the model with the complexity of the model, penalizing models with more parameters to prevent overfitting. The formula for AIC is $AIC equals minus 2 backslash ln L plus 2k$, where $L is the maximum likelihood of the model. $K$ is the number of parameters in the model. A lower AIC value suggests a better model. When comparing multiple ARMA, P, Q models, we typically fit a range of plausible code snippet and code snippet values and select the combination that yields the lowest AIC. For our bandwidth data, we will iterate through a range of code snippet, AR order, and code snippet, MA order, values, fit an ARMA model with $D equals $1 for differencing, and record the AIC for each combination. Download the code on one patch code Substack. This code performs a grid search over specified code snippet and code snippet values. For each combination, it attempts to fit in code snippet model using code snippet. The code snippet is fixed at 1, as determined by our stationarity test. It prints updates as it finds a better model, lower AIC, and finally outputs the optimal order and the top 5 models by AIC. In a real-world scenario, you might also consider the Bayesian Information Criterion, BC, which penalizes complexity more heavily than AIC, often leading to simpler models. 5. Model validation with residual analysis. After selecting the optimal ARMA model, it's crucial to validate its adequacy. A well-fitted time series model should produce residuals that resemble white noise. White noise residuals imply that the model has captured all the significant patterns and dependencies in the data, leaving only random, unpredictable fluctuations. Characteristics of white noise residuals. 1. Zero mean. The residuals should fluctuate randomly around 0. 2. Constant variance. The spread of residuals should be consistent over time. Homoscedasticity. 3. No autocorrelation. There should be no significant correlation between residuals at different lags. This is the most critical check for time series models. 4. Normal distribution. Residuals should ideally be normally distributed, especially for constructing confidence intervals for forecasts. We can assess these characteristics by examining several diagnostic plots and statistical tests. Correlogram, ACF of residuals. This plot should show no significant spikes, i.e., all bars within the confidence intervals, indicating no remaining autocorrelation. QQ plot, quantile plot, compares the quantiles of the residuals to the quantiles of a theoretical normal distribution. If the residuals are normally distributed, the points should fall approximately along a straight line. Density plot, histogram of residuals, shows the distribution of the residuals. It should resemble a bell curve for normally distributed residuals, centered around 0. Ljung box test, a formal statistical test for overall autocorrelation in the residuals. The null hypothesis is that the residuals are independently distributed, i.e., no autocorrelation. A high p-value, e.g., greater than 0.05, indicates that we cannot reject the null hypothesis, suggesting that the residuals are indeed white noise. Let's fit the best model identified by AIC and then perform residual analysis using code snippet. Download the code on one patch code Substack. This code fits the code snippet model with the code snippet found in the previous step and prints its summary, which includes various statistics, coefficients, and the AIC/BIC values. The code snippet method conveniently generates 4 plots. Standardized residuals shows the residuals over time. Look for constant variance and no obvious patterns. Histogram plus KDE estimate shows the distribution of residuals. Should be bell-shaped and centered at 0. Normal QQ plot. Points should follow the red straight line for normality. Correlogram, ACF, of residuals. All bars should ideally be within the blue confidence intervals, indicating no significant autocorrelation. Interpreting Figure 6.5. Standardized residuals. The plot should show random scatter around 0, with no obvious trends or increasing/decreasing variance. Our plot likely shows this, indicating homoscedasticity. Histogram plus KD. The histogram should be roughly symmetric and bell-shaped, centered at 0. The kernel density estimate, KD, line should closely follow the histogram bars. Normal QQ plot. The points should lie close to the 45-degree line. Deviations, especially at the tails, indicate departures from normality. While ideal for forecasts, strict normality is less critical than lack of autocorrelation for model validity. Correlogram, ACF, of residuals. This is the most important plot. Ideally, all blue bars should be within the light blue shaded region, indicating that the residuals are uncorrelated and thus white noise. If there are significant spike, it means our model has not captured all the autocorrelation in the data, and we may need to refine the model, e.g., try different code snippet or code snippet orders, or consider seasonal components if they haven't been accounted for. Finally, we can perform the Ljung box test to formally check for autocorrelation in the residuals. Download the code on one PACF Substack. The code snippet function performs the test. We typically look at the p-value, code snippet. If this p-value is greater than our significance level, e.g., 0.05, we conclude that there is no significant autocorrelation in the residuals, supporting the adequacy of our model. If the p-value is small, it suggests that the model is not fully capturing the underlying patterns. 6. Forecasting future bandwidth usage. With a validated model, we can now generate forecasts for future bandwidth usage. This is the ultimate goal of our analysis, providing actionable insights for data center resource management. The code snippet method of the fitted code snippet model can be used for this purpose. When forecasting, it's good practice to also generate confidence intervals. These intervals provide a range within which the actual future values are expected to fall, giving a measure of uncertainty around our point forecasts. Wider intervals imply greater uncertainty. Download the code on one PACF Substack. This segment sets up the forecast horizon, 7 days in our case, and generates future dates. It then uses the snippet to obtain both the point forecasts, code snippet, and the 95% confidence intervals, code snippet. The output shows the first few forecasted values and their corresponding confidence bounds. Finally, visualizing the forecasts against the historical data provides a clear picture of the model's predictive capability. Download the code on one PACF Substack. This final plotting code generates figure 6.6, which is crucial for visualizing the model's performance. It overlays the historical data with the forecasted values and their confidence intervals. For data center operators, this visual representation is highly valuable. It allows them to see potential future peaks in demand, understand the uncertainty associated with those predictions, and make informed decisions about scaling resources up or down. For instance, if the upper bound of the forecast confidence interval approaches the current capacity limits, it signals a need to provision more resources. Conversely, if the forecast suggests a sustained period of low usage, it might indicate an opportunity to shut down non-essential servers to save energy and costs. While not explicitly covered in this section, in a production environment, you would also evaluate forecast accuracy using metrics like root mean squared error, RMSE, or mean absolute error, and by comparing forecast against actual observed values in a holdout test set. This continuous evaluation helps refine and improve forecasting models over time. The previous sections established the foundational concepts of autoregressive, AR, and moving average, MA, processes, highlighting their individual strengths and limitations in modeling time series data. While AR models capture dependencies on past values of the series itself, MA models account for dependencies on past forecast errors. Many real-world time series exhibit characteristics of both, necessitating a more comprehensive modeling approach. This is where the Autoregressive Moving Average, ARMA, process comes into play. The ARMA, PQ, process, a unified approach. The ARMA model is a powerful statistical tool that combines the autoregressive AR and moving average MA components into a single framework. It is particularly effective for modeling stationary time series data, that display both autoregressive and moving average characteristics. An ARMA model is denoted as ARMA PQ, where code snippet represents the order of the autoregressive AR part. This indicates the number of past observations of a series that are included in the model. Code snippet represents the order of the moving average MA part. This indicates the number of past forecast errors, or white noise terms, that are included in the model. By combining these two aspects, the ARMA model can capture a broader range of complex temporal dependencies than either an AR or an MA model alone. Mathematical formulation of ARMA PQ. The general mathematical equation for an ARMA PQ process is given by $YT equals C plus backslash sum I equals 1 caret P backslash phi YTI plus backslash so J equals 1 caret Q backslash the Taj backslash epsilon TJ plus backslash epsilon dollar. Let's break down each component of this equation. $YT dollar. This represents the value of the time series at the current time point code snippet. It is the value we're trying to model or forecast. $C dollar. This is a constant term, often referred to as the intercept. It captures the baseline level of the series when all other effects are zero. In some formulations, especially when the series is modeled around its mean, this constant code snippet might be related to or absorbed by the mean code snippet, mu, of the series. For a series with mean code snippet, the equation can also be written as $YT backslash mu equals backslash sum I equals 1 caret P backslash phi YTI backslash mu plus backslash sum J equals 1 or backslash the Taj backslash epsilon TJ plus backslash epsilon dollar. Or, equivalently, by rearranging the terms. $YT equals backslash mu 1 backslash sum I equals 1 caret P backslash phi plus backslash sum I equals 1 or P backslash phi YTI plus backslash so J equals 1 or Q backslash the Dodge backslash epsilon TJ plus backslash epsilon dollar. In this form, the constant term $C equals backslash mu 1 backslash sum I equals 1 caret P backslash phi dollar. Understanding this relationship helps prevent confusion when encountering different notations for the constant or mean. Backslash sum I equals 1 caret P backslash phi YTI dollar. This is the autoregressive AR part of the model. Backslash phi dollar. Phi, these are the autoregressive coefficients. Each backslash phi dollar quantifies the linear dependence of $YT dollar on its past value $YTI dollar. For example, backslash phi $1 relates to $YT $1, backslash phi $2 to $YT $2, and so on, up to $P dollar lag values. These coefficients determine how STR. Only past observations influence the current observation. $YTI of dollar. These are the past observed values of the time series at lag's code snippet. The sum indicates that $YT dollar depends on a linear combination of its previous $P dollar values. Backslash sum J equals 1 caret Q backslash the Taj backslash epsilon TJ dollar. This is the moving average in May, part of the model. Backslash theta dollar. Theta, these are the moving average coefficients. Each backslash theta dollar quantifies the linear dependence of $YT dollar on past forecast errors backslash epsilon TJ dollar. Note that some conventions use a negative sign before the sum for the MA part, e.g., $YT equals backslash epsilon, backslash sum backslash the Taj backslash epsilon TJ dollar. But the form shown here is also widely used and simply implies that the sign is absorbed into the backslash theta dollar coefficient itself. These coefficients dictate how past unpredictable shocks propagate through the series. Backslash epsilon TJ dollar. These are the past error terms, or white noise shocks, at lag's code snippet. These represent the unobservable random disturbances that occurred at previous time points, effectively accounting for the memory of past forecast errors. Backslash epsilon dollar. This is the current error term at time code snippet. It represents the white noise shock at the current time point, which is not explained by the AR or MA components. It is crucial to the model's validity that these error terms are assumed to be white noise. This means they are independently and identically distributed ID, with a mean of 0 and a constant variance, $\sigma$2, and no auto correlation. This assumption ensures that all systematic information has been captured by the AR and MA parts of the model, leaving only random, unpredictable noise. Understanding the coefficients. The coefficients $\phi$ and $\theta$ are the parameters that the model estimates from the historical data. They determine the strength and direction of the relationships between the current value and its past observations or past errors. Consider a conceptual representation of how these coefficients combine to form the components of the ARMA model. Download the code on one PACF Substack. This first chunk outlines the structure of the autoregressive component. It shows how each pass code snippet value is weighted by its corresponding code snippet coefficient, and these weighted values are summed. Download the code on one PACF Substack. This second chunk focuses on the moving average part, demonstrating how past error terms are similarly weighted by code snippet coefficients and summed. Download the code on one PACF Substack. Finally, this segment shows how the constant, the calculated AR component, the calculated MA component, and the current error term combine to yield the current value of the time series, $YT$. This conceptual building block approach helps in understanding the model structure. Special cases, ARMA as generalization. The beauty of the ARMA, PQ, model lies in its generality. It encompasses both pure AR, P, and pure MA, Q, models as special cases. The ARMA, P0, simplifies to an AR, P process. When code snippet, the moving average part, $\sum J equals 1 Q the Taj epsilon J $, vanishes because the sum goes up to code snippet, meaning no terms are included. The equation becomes $YT equals C plus sum I equals 1 P phi YTI plus epsilon $. This is precisely the definition of an autoregressive process of order code snippet. The ARMA 0 Q simplifies to an MA Q process. When code snippet, the autoregressive part $sum I equals 1 phi YTI vanishes for the same reason. The equation becomes $est égal C plus sum J égale 1 Q tétage epsilon TJ plus epsilon $. This is the definition of a moving average process of order code snippet. This demonstrates that ARMA models provide a flexible framework capable of representing a wide range of time series behaviors by simply adjusting the order's code snippet and code snippet. Illustrative examples. Let's look at specific examples of ARMA models to solidify understanding. ARMA 1-1 model. An ARMA 1-1 model has one AR term, P equals 1, and one MA term, Q equals 1. Its equation is $est égal C plus phi 1 Y T moins 1 ou plus θ 1 epsilon T moins 1 ou plus epsilon $. Here, the current value $YT$ depends on its immediate past value $Y, $1, autoregressive influence, and the immediate past error term $epsilon T, $1, moving average influence, in addition to the constant and the current error. This model is often a good starting point for simple, yet effective, time series modeling, as it captures the most direct past dependencies. ARMA 2-1 model. An ARMA 2-1 model includes two AR terms, P equals 2, and one MA term, Q equals 1. $est égal C plus phi 1 Y T moins 1 U plus phi 2 Y T moins 2 U plus θ 1 epsilon T moins 1 plus epsilon $. In this case, $YT$ depends on its values from two previous time steps, $YT $1 and $YT $2, and the error from the previous time step, $epsilon T $1. This added complexity allows the model to capture more intricate patterns of dependence, such as a decaying influence from observations further in the past. Stationarity requirement. A critical assumption for the ARMA model and its AR and MA components to be stable and have well-defined statistical properties is stationarity. While a full exposition of stationarity was covered in previous sections, it's vital to remember that for an ARMA PQ model to be valid and invertible, its underlying AR part must be stationary, and its MA part must be invertible. Stationarity implies that the statistical properties of the time series, mean, variance, autocorrelation structure, do not change over time. This is crucial because it allows us to use past data to make inferences about future behavior, assuming the underlying process remains consistent. Invertibility ensures that an MA process can be represented as an infinite AR process and vice versa. This property is important for model identification, parameter estimation, and ensuring a unique model representation. If a time series is not stationary, it must be transformed, e.g., differenced, to achieve stationarity before an ARMA model can be appropriately applied. This leads to the concept of ARMA models, which will be discussed in a later section, specifically designed to handle non-stationary series. The challenge of model identification. One common pitfall when working with ARMA models is the difficulty in determining the appropriate code snippet and code snippet orders from the autocorrelation function, ACF, and partial autocorrelation function, PACF, plots alone. As discussed in previous sections, for a pure AR-P process, the ACF typically decays exponentially or sinusoidally, while the PACF cuts off sharply after lag code snippet. For a pure MA-Q process, the PACF typically decays exponentially or sinusoidally, while the ACF cuts off sharply after lag code snippet. However, for an ARMA PQ process, both the AR and MA components contribute to the observed autocorrelation structure. This means that both the ACF and PACF plots for an ARMA model will typically show a mix of exponential decay and sinusoidal patterns, without a clear sharp cutoff in either. The effects of the AR and MA parts are convolved or intertwined in these plots, making visual identification of code snippet and code snippet ambiguous and challenging. It's like trying to discern two overlapping musical melodies from their combined sound. To address this, more sophisticated model selection criteria are employed. While we won't delve into them here, it's important to be aware that tools like the Eichen Forma, Tying Criterion, AIC, and the Bayesian Information Criterion, BC, are commonly used to compare different ARMA models and select the best-fitting one based on a balance between model complexity and goodness of fit. These criteria penalize models for having too many parameters, guiding us towards the simplest model that adequately explains the data. These criteria will be explored in detail in subsequent chapters dedicated to model identification and selection. Practical application, bandwidth usage forecasting. As introduced in the preceding chapter, forecasting bandwidth usage for data centers is a prime example of where ARMA models can be invaluable. Bandwidth consumption often exhibits both dependence on past usage patterns, autoregressive behavior, and on random fluctuations or external shocks, moving average behavior, like sudden traffic spikes or network outages. A pure AR or MA model might only capture a part of this dynamic. By employing an ARMA PQ model, we can potentially achieve more accurate forecasts by simultaneously accounting for these interwoven dependencies, leading to better resource allocation, proactive scaling of infrastructure, and improved operational planning within data centers. This theoretical foundation sets the stage for applying these models to real-world data in upcoming sections. Identifying a stationary ARMA process. Identifying the specific orders, P, Q, of an autoregressive moving average, ARMA, process from its autocorrelation function, ACF, and partial autocorrelation function, PACF, plots presents a unique challenge compared to pure autoregressive, AR, or moving average, MA, processes. While AR processes have a decaying ACF and a sharp cutoff in PACF, and MA processes exhibit a sharp cutoff in ACF and a decaying PACF, an ARMA process combines both effects. This combination often results in both the ACF and PACF displaying decaying or sinusoidal patterns, making it difficult to pinpoint the exact orders P, Q by visual inspection alone. The goal in this section is not to find a definitive cutoff, but to recognize the absence of one in both plots, signaling the presence of an ARMA process. This understanding is crucial for correctly modeling complex time series, such as the bandwidth usage data we've been discussing, which rarely conform to simple AR or MA structures. Simulating an ARMA P-Q process. To illustrate the characteristics of an ARMA process, we will simulate a simple ARMA 1-1 series. This allows us to control the underlying parameters and observe the resulting ACF and PACF patterns without the noise and complexity of real-world data initially. We begin by importing the necessary libraries: code snippet for numerical operations, code snippet for plotting, and code snippet for simulating the time series, along with code snippet code snippet and code snippet for analysis and visualization. Download the code on one patch code Substack. Setting a random seed code snippet is a standard practice in simulations. It ensures that every time you run the code, the random numbers generated are the same, leading to identical simulation results. This is invaluable for debugging, sharing code, and ensuring that your analyses are reproducible. Next, we define the coefficients for our ARMA 1-1 process. An ARMA 1-1 process has one autoregressive term, P equals 1, and one moving average term, Q equals 1. Download the code on one patch code Substack. A critical detail when working with code snippet is the sign convention for the AR coefficients and the inclusion of the lag zero coefficient. AR coefficients code snippet. The code snippet array represents the coefficients of the AR polynomial code snippet, where code snippet is the lag operator. If your AR model is typically written as $YT equals \phi1y 1 plus \phi2YT 2 plus \epsilon$, then you must provide the coefficients with opposite signs to code snippet. For an AR1 with $\phi1 equals 50 cents, the polynomial is $1 $0.5L, so we provide code snippet. The leading code snippet in code snippet represents the coefficient of $YT itself, i.e., at lag 0, in the polynomial, which is always 1. MA coefficients code snippet. For MA coefficients, code snippet expects them as they appear in the MA polynomial code snippet. If your MA model is $YT equals \epsilon plus \theta 1 \epsilon 1 plus \theta 2 \eps, $2, then you provide code snippet. Again, the leading code snippet in code snippet represents the coefficient of $epsilon$ at lag 0. Finally, we generate a sample from our defined ARMA process. Download the code on one patch code Substack. The code snippet method creates the time series. The code snippet parameter is crucial. It discards an initial number of observations. This helps ensure that the generated series has stabilized and is truly representative of the stationary process, removing any transient effects from the arbitrary starting values. A longer code snippet period is generally safer for more complex models. The simulated ARMA 1-1 time series will visually appear stationary, meaning its statistical properties, mean, variance, autocorrelation, do not change over time. It will fluctuate around a constant mean with constant variance, without obvious trends or increasing/decreasing volatility. Ensuring stationarity. The augmented Dickey-Fuller ADF test. Before analyzing the ACF and PACF plots, it's essential to confirm that our simulated time series is indeed stationary. The augmented Dickey-Fuller ADF test is a widely used statistical test for this purpose. Download the code on one patch code Substack. The ADF test helps us formally check for stationarity. Null hypothesis, $H0 the time series has a unit root, meaning it is non-stationary, e.g., it has a trend or random walk component. Alternative hypothesis, $H1 the time series does not have a unit root, meaning it is stationary. If the p-value from the ADF test is less than or equal to a chosen significance level, commonly 0.05, we reject the null hypothesis and conclude that the time series is stationary. For our simulated ARMA 1 process, which is designed to be stationary, we expect a low p-value. Lags. Download the code on one patch code Substack. Similarly, the PACF for an ARMA 1 process also typically exhibits a decaying or sinusoidal pattern, rather than a sharp cutoff after the first lag, as seen in pure AR1. This is because the MA component introduces a decaying partial autocorrelation structure, which interacts with the AR component's direct impact. Mathematical intuition for ARMA ACF/PACF patterns. In an ARMA process, the current value $YT is influenced by both its own past values and past error terms. The AR component, e.g. $YT equals \phi1YT 1 plus \epsilon$, creates a decaying ACF because the influence of past $Y values gradually diminishes. It creates a sharp cutoff in PACF because once the direct effect of $Y to $1 is accounted for, $Y to $, has no additional direct effect on $YT. The MA component, e.g. $YT equals \epsilon plus \theta 1 \epsilon $1, creates a sharp cutoff in ACF because the direct impact of past errors only extends to the specified MA order. It creates a decaying PACF because the indirect effects of past errors propagate through the system. When both are combined in an ARMA process, their effects are superimposed. The AR part blurs the MA cutoff in the ACF, causing it to decay, and the MA part blurs the AR cutoff in the PACF, causing it to decay. The result is that neither plot shows a clear, sharp cutoff. Instead, both display patterns that gradually fade to zero, often with oscillating or sinusoidal behavior, indicating a mix of AR and MA characteristics. This lack of a clear cutoff in both plots is the signature of an ARMA process. Comparison pure AR1 ma 1 versus ARMA 1,1. To reinforce the concept of no clear cutoffs for ARMA processes, let's briefly simulate and plot the ACF and PACF for pure AR1 and MA1 processes for direct comparison. Download the code on one patch code Substack. Observe the plots for the pure AR1 process. The ACF decays exponentially, while the PACF shows a sharp cutoff after the first lag, meaning only the first partial autocorrelation is significant. This is the classic signature of an AR1 process. Download the code on one patch code Substack. For the pure MA1 process, the roles are reversed. The ACF shows a sharp cutoff after the first lag, while the PACF decays exponentially. This is the classic signature of an MA1 process. By comparing these pure AR and MA plots with the ARMA 1 plots, the blurring effect of combining AR and MA components becomes evident. The ARMA 1 plots show decaying patterns in both ACF and PACF, without the distinct cutoff seen in their pure counterparts. This is the key visual cue for identifying an ARMA process. Connecting to real-world applications. The simulated ARMA 1 process, while simplified, mimics the complex autocorrelation structures often found in real-world time series data. Consider the hourly bandwidth usage data discussed previously. Bandwidth consumption at any given hour is likely influenced by passband. With usage, AR component high usage in the previous hour might indicate continued high demand, reflecting a structural dependency. Past unpredictable events or shocks. MA component, a sudden surge in usage might be due to a transient event, e.g., a software update release, a popular video going viral, whose effect is felt for a short period and then fades, representing the moving average component. Such real-world data rarely fit neatly into a pure AR or MA model. Instead, they often exhibit characteristics that are best captured by an ARMA process, where both the autoregressive and moving average dynamics are at play. Other common scenarios where ARMA processes are frequently encountered include financial market data. While often non-stationary and requiring differencing, leading to ARMA, the difference series, returns, can exhibit ARMA properties, reflecting market memory and short-term shocks. Environmental sensor readings, temperature, pollution levels, or river flow rates can show both dependencies on past readings and responses to immediate, transient environmental events. Economic indicators, inflation rates, unemployment figures, or GDP growth often have complex dependencies on their own past values and past economic shocks. Recognizing the decaying patterns in both ACF and PACF plots, coupled with formal tests like the ADF test to confirm stationarity, serves as the primary diagnostic tool for identifying that an ARMA process is a suitable candidate mod. L for your time series data. This understanding then paves the way for more rigorous model selection techniques, such as using information criteria, AIC, BC, to determine the optimal orders, P, Q, devising a general modeling procedure. While the autoregressive, AR, and moving average, MA, processes have distinct characteristics in their autocorrelation function, ACF, and partial autocorrelation function, PACF plots. AR processes show a cutoff in PACF and exponential decay in ACF, while MA processes show a cutoff in ACF and exponential decay in PACF. The situation becomes significantly more complex for combined autoregressive moving average, ARMA, processes. The limitations of visual identification for ARMA processes. For an ARMA, PQ process, both the autoregressive and moving average components simultaneously influence both the ACF and PACF plots. This superposition of effects means that neither plot typically exhibits a clear, sharp cutoff. Instead, both the ACF and PACF for an ARMA, PQ process will often show a decaying or oscillatory pattern. AR component influence. The AR part of the model, order code snippet, tend to induce exponential decay or sinusoidal patterns in the ACF. MA component influence. The MA part of the model, order code snippet, tends to induce exponential decay or sinusoidal patterns in the PACF. Combined effect. When both are present, the combined effect is that both the ACF and PACF plots will exhibit complex decaying or oscillating patterns, making it exceedingly difficult to visually determine the precise orders code snippet and code snippet by looking for a cutoff. This is a common pitfall for new analysts, as the intuitive visual ID identification method that works for pure AR or MA models breaks down. Because of this inherent ambiguity, a more systematic, quantitative, and iterative approach is required to identify the appropriate orders for an ARMA, PQ model. A systematic modeling procedure for ARMA, PQ. The following procedure provides a robust framework for identifying and validating ARMA models, especially when visual inspection of ACF/PACF plots is inconclusive. It emphasizes an algorithmic and iterative approach, leveraging statistical criteria and diagnostic tests. Step 1. Data preparation and stationarity check. Before any modeling, ensure your time series data is stationary. This typically involves visual inspection, plotting the series to check for trends, seasonality, and varying variance. Statistical tests, using tests like the augmented Dickey-Fuller ADF test to formally check for unit roots. Differencing, if non-stationary, applied differencing, e.g., first-order differencing for trends, seasonal differencing for seasonality, until the series becomes stationary. The number of differences applied will determine the integrated part in an ARMA model, which we will cover in detail later. For now, assume the series is code snippet or has been made stationary. Step 2. Initial exploration of PQ orders. Since visual identification is unreliable, we resort to systematically exploring a range of possible code snippet combinations. Define search space. Choose a reasonable range FO. Are code snippet and code snippet Common starting points involve code snippet and code snippet values from 0 up to 3, 4, or 5. For example, code snippet is an element of code snippet, and code snippet is an element of code snippet. Computational implications. Be aware that fitting every combination can be computationally intensive. If code snippet is 3 and code snippet is 3, you're fitting code snippet models. For larger ranges, say code snippet, you'd fit code snippet models. This emphasizes the need for efficient computation and possibly parallel processing for very large datasets or wider search spaces. Step 3. Model fitting and selection using AIC. For each code snippet combination within your defined search space, fit an ARMA model to the stationary time series data. The primary criterion for selecting the best model among these candidates is often the Akaika Information Criterion, AIC. What is AIC? The Akaika Information Criterion, AIC, is a widely used metric for model selection. It estimates the relative quality of statistical models for a given set of data. AIC provides a means for model comparison, balancing the goodness of fit of the model with the complexity of the model, i.e., the number of parameters used in the model. Formula: simplified concept code snippet. Code snippet: the number of estimated parameters in the model. This term penalizes model complexity. Code snippet: the natural logarithm of the maximum likelihood estimate for the model. This term rewards goodness of fit. Interpretation: when comparing multiple candidate models, the model with the lowest AIC value is generally preferred. This is because a lower AIC indicates a better balance between fit and complexity. A model that fits the data very well but uses too many parameters over fits will be penalized, as will a model that is too simple and doesn't capture enough of the data's patterns. Let's illustrate a conceptual comparison of AIC values for different models. In practice, statistical software libraries will compute AIC for you. Download the code on one patch code Substack. This initial code block sets up a simulated dataset that we can use to demonstrate model fitting and AIC comparison. In a real-world application, code snippet would be your pre-processed stationary time series. Now let's conceptualize fitting two different ARMA models to this data and comparing their AIC scores. Download the code on one patch code Substack. This block demonstrates how you would fit different ARMA models using code snippet and extract their AIC values. We've included the true model, ARMA 1-1, from our simulation to show how its AIC often compares favorably. In a real application, you would store all calculated AIC values and then programmatically select the code snippet pair that yielded the minimum AIC. Download the code on one patch code Substack. This final part of the conceptual example illustrates the decision-making process. After fitting multiple models, you would identify the one with the lowest AIC. This model becomes your primary candidate for further validation. Step 4. Residual analysis for model validation. Once a candidate model has been selected based on AIC, the next crucial step is to validate its adequacy by analyzing its residuals. The residuals, the difference between the observed values and the model's predictions, should ideally behave like white noise. This means they should be uncorrelated, have a constant variance, and a zero mean. If the residuals are not white noise, it indicates that the model has not captured all the underlying patterns in the data, and there's still information left to be modeled. Two primary tools for residual analysis are 1. QQ-plot, quantile plot. Purpose: to check if the residuals are normally distributed, a common assumption for many time series models, particularly for the error term. Interpretation: if the residuals are normally distributed, the points on the QQ plot will roughly lie along a 45-degree line. Deviations from this line, especially at the tails, suggest non-normality. 2. Ljungbox test, portmanteau test. Purpose: to test for the presence of autocorrelation in the residuals. It tests the null hypothesis that there is no autocorrelation up to a specified number of lags. Interpretation: a high p-value, typically code snippet, for the Ljungbox test indicates that you cannot reject the null hypothesis, meaning there is no significant autocorrelation in the residuals. This supports the conclusion that the residuals are white noise. Conversely, a low p-value code snippet suggests that significant autocorrelation remains, indicating that the model is inadequate. Let's demonstrate how to perform residual analysis conceptually. Download the code on one PACF Substack. This chunk ensures we have a code snippet object, a fitted model, for which we can extract the residuals. The code snippet attribute of the results object contains the time series of residuals. Now, let's plot the QQ plot and the ACF/PACF of the residuals. Download the code on one PACF Substack. This code generates the visual diagnostic plots. The QQ plot helps assess normality, and the ACF/PACF plots of the residuals visually confirm if there's any remaining autocorrelation. Ideally, all spikes in the ACF/PACF plots should fall within the blue shaded confidence intervals. Finally, we perform the Ljung box test for a formal statistical check of residual autocorrelation. Download the code on one PACF Substack. The Ljung box test provides a quantitative measure. A high p-value, typically above 0.05, across various lags is the desired outcome, confirming that the residuals are statistically indistinguishable from white noise. This is a strong indicator that your model has adequately captured the temporal dependencies in the data. Step 5. Iteration and refinement. If the residual analysis indicates that the residuals are not white noise, e.g., QQ plot shows significant deviations, or Ljung box test yields low p-values, it means your chosen ARMA model is not yet adequate. This is where the iterative nature of modeling comes into play. Expand search space, revisit step 2, and try a wider range of code snippet and code snippet values. Perhaps the optimal model was outside your initial search. Reevaluate stationarity. Double-check if the series is truly stationary. Sometimes, an initial differencing might not be sufficient, or too much differencing could have been applied, leading to an over-difference series. Consider seasonal components. If the series exhibits seasonality, an ARMA model alone might not be sufficient. You might need to consider a seasonal ARMA model, which explicitly accounts for seasonal patterns. This will be covered in later sections. External regressors. If there are external factors influencing the time series, consider incorporating them as exogenous variables into your model, Armax or Ceramax. Alternative models. If ARMA models consistently fail, explore other types of time series models, such as GRCH for volatility modeling or state space models for more complex structures. Domain knowledge. Always leverage your understanding of the underlying process generating the data. Sometimes, domain-specific insights can guide you to better model choices or transformations. This systematic procedure, combining quantitative criteria like AIC with rigorous residual diagnostics, provide a robust framework for identifying and validating ARMA models, moving beyond the limitations of purely visual identification. Practical considerations and best practices. Computational cost. Be mindful of the computational resources required when searching a wide range of code snippet orders, especially for very long time series. Parsimony. While AIC helps, always lean towards the simplest model that adequately explains the data. A simpler model is often more interpretable and less prone to overfitting, especially for forecasting. Forecast performance. Ultimately, the best model is the one that provides the most accurate and reliable forecasts. After selecting a model, it's crucial to evaluate its out-of-sample forecasting performance using techniques like walk-forward validation. Automated tools. Libraries like Code Snippet, a Python package that provides an code snippet function, can automate much of this iterative process by systematically searching for optimal code snippet orders based on AIC or BHC, and performing stationarity checks. While powerful, understanding a manual procedure is essential for debugging and fine-tuning. 6.4.1 Understanding the Aikaika Information Criterion, AIC. In the pursuit of devising a robust general modeling procedure for time series, we often face a critical challenge. How do we select the best model from a set of plausible candidates? While visual tools like ACF and PACF plots provide initial guidance, they can be subjective and less precise when distinguishing between closely related ARMA processes. This is where quantitative criteria become indispensable. The Archaic Information Criterion, AIC, stands out as a widely adopted and highly effective tool for this purpose. The AIC provides a quantitative measure to evaluate and compare statistical models. Its fundamental goal is to identify the model that best describes the data while simultaneously penalizing for model complexity. This dual objective helps to strike a balance between model fit and parsimony, preventing both underfitting, models too simple to capture the data structure, and overfitting, models too complex, capturing noise rather than true patterns. The AIC formula and its components. The Archaic Information Criterion, AIC, is mathematically defined as $IC égale 2K, 2 ln, L, $. Let's break down each component of this formula. Code snippet. Number of parameters. This term represents the number of estimated parameters in the statistical model. It serves as the penalty for model complexity. In the context of an ARMA, PQ model, code snippet typically includes code snippet autoregressive parameters, $phi1, dots, $fip. Code snippet moving average parameters, $theta1, dots, $thetac. A constant term, if included in the model. The variance of the error term, $sigma, $2. For instance, an ARMA 1 model with a constant term would have code snippet parameters. The more parameters a model has, the higher its complexity, and thus, the larger the penalty term code snippet. Code snippet. Maximum likelihood. This represents the maximum value of the likelihood function for the estimated model. The likelihood function quantifies how probable it is to observe the given dataset under the assumption that the data was generated by the specific model with its estimated parameters. A higher code snippet indicates a better fit of the model to the data. To understand code snippet, consider the concept of maximum likelihood estimation, MLE. MLE is a common method used to estimate the parameters of a statistical model. It works by finding the parameter values that maximize the likelihood function, effectively making the observed data as probable as possible. For example, if you have a series of stock returns, MLE would find the ARMA parameters that make the occurrence of those specific returns most likely. The value of the likelihood function at these optimal parameters is the code snippet we use in the AIC formula. Code snippet. This part of the formula quantifies the goodness of fit. Since code snippet is a probability or product of probabilities, its value is typically between 0 and 1. The natural logarithm code snippet will therefore be a negative number. Multiplying by code snippet makes this term positive. A larger code snippet, better fit, results in a smaller code snippet closer to 0, and thus a smaller positive code snippet term. This means a better fitting model contributes a smaller value to the overall AIC. Interpreting AIC values. The goal when using AIC is to select the model with the lowest AIC value. A lower AIC indicates a better balance between model fit and complexity. Balancing act. The code snippet term penalizes complexity, while the code snippet term rewards goodness of fit. A very complex model, large code snippet, might achieve a slightly better fit, larger code snippet, meaning smaller code snippet, but the penalty from code snippet could outweigh this improvement, leading to a higher AIC. This prevents overfitting. A very simple model, small code snippet, might have a low complexity penalty, but a poor fit, small code snippet, meaning larger code snippet, would result in a high AIC. This prevents underfitting. Relative comparison. It's crucial to understand that AIC values are not absolute measures of model quality. They are relative. You cannot say a model with an AIC of 100 is good in isolation. You can only say it's better than a model with an AIC of 110 for the same dataset. AIC is used for comparing models fitted to the same data. Information lost. AIC is rooted in information theory and is an estimate of the information lost when a given model is used to represent the process that generated the data. The model with the lowest AIC is considered to be the one that loses the least amount of information, thus providing the best approximation of the true underlying process. Other information criteria, BGC and HQIC. While AIC is widely used, other information criteria exist, most notably the Bayesian Information Criterion, BC, and the Hannon-Quinn Information Criterion, HQIC. They share the same objective, but differ in how they penalize complexity. BC, $BC equals K \ln N to ln L, where code snippet is the number of observations. BIC imposes a stronger penalty for complexity than AIC, especially for larger datasets. This often leads BIC to select simpler models. Hot duakaon and duon L. Kick's penalty lies between AIC and BIC. The choice between AIC, BC, and HQIC often depends on the specific application and theoretical preferences. For forecasting, AIC is generally favored, while BC is often preferred when the goal is to identify the true underlying model from a set of candidates. Practical application: grid search for optimal PQ using AIC. One of the most powerful applications of AIC in time series analysis is its use in systematically identifying the optimal orders PQ for an ARMA model. Instead of relying solely on subjective interpretation of ACF/PACF plots, we can perform a grid search, fitting ARMA models for a range of code snip T and code snippet values, and then selecting the combination that yields the lowest AIC. Let's walk through a Python example using code snippet to demonstrate this process. We'll start by simulating a simple ARMA 1.1 process to have some data to work with. First, we need to import the necessary libraries. Download the code on OnePageCode Substack. We import code snippet for data handling, code snippet for numerical operations, and code snippet for time series modeling. Specifically, code snippet from code snippet is the recommended class as it unifies ARMA, ARMA, and ARMA models. We also suppress warnings that might arise from models that fail to converge during our grid search. Next, let's simulate a time series that follows an ARMA 1.1 process. This will give us a true model to compare our findings against. Download the code on OnePageCode Substack. Here, we simulate 200 data points from an ARMA 1.1 process with known coefficients. This allows us to later verify if our AIC-based selection correctly identifies the underlying process. Note the code snippet and code snippet parameter conventions for code snippet and code snippet. Now, we define the range of code snippet and code snippet values we want to test. It's common practice to start with small integers, as higher orders drastically increase computational time and complexity. Download the code on OnePageCode Substack. We'll test code snippet and code snippet from 0 to 2, which covers AR 0 to AR2, MA0 to MA2, and all combinations up to ARMA 2. The core of our grid search involves nested loops. For each code snippet combination, we'll fit and code snippet model, with code snippet to make it an ARMA model and extract its AIC. We'll store these results to find the minimum AIC later. Download the code on OnePageCode Substack. In this block, we initialize an empty dictionary code snippet to store the AIC for each code snippet pair. Nested code snippet loops iterate through all combinations of code snippet and code snippet. We skip code snippet because it's a trivial model, just a constant or white noise. Inside the loop, we use a code snippet block to gracefully handle potential errors during model fitting, e.g., non-convergence, assigning code snippet infinity as the AIC for failed models. Code snippet specifies an ARMA PQ model by setting the differencing order code snippet to 0. Code snippet estimates the model parameters. Code snippet directly provides the AIC value for the fitted model. Finally, we identify the code snippet combination that resulted in the lowest AIC. Download the code on one PACF Substack. This code snippet uses code snippet to find the key, the code snippet tuple, associated with the minimum value in the code snippet dictionary. Prints the optimal code snippet and its corresponding AIC. Converts the results into a code snippet data frame and sorts them by AIC, providing a clear overview of all tested models and their AIC score. For our simulated ARMA 1.1 data, this grid search should ideally identify code snippet as the optimal code snippet pair, demonstrating AIC's effectiveness in recovering the true underlying process. If the results are slightly off, e.g., 1, 0, or 0, 1, it could be due to the limited sample size or the specific random realization of the simulated series. Visualizing AIC values. Visualizing the AIC values across the grid of code snippet combinations can provide further insight into the model selection landscape. A heat map or a 3D plot can clearly show which combinations yield lower AICs. Download the code on one PACF Substack. This visualization helps us quickly identify regions of lower AIC values and understand the trade-offs between different code snippet and code snippet orders. The darkest cell in the heat map will correspond to the optimal model. Common pitfalls and best practices. While AIC is a powerful tool, it's important to use it judiciously. 1. Stationarity is key. AIC assumes that the underlying time series is stationary. Before applying ARMA models and using AIC for selection, ensure your data is stationary or has been made stationary through differencing. 2. Relative, not absolute. Remember that AIC is for relative comparison. A low AIC indicates a better model among the candidates tested, not necessarily a perfect model or a good absolute fit. 3. Consider residuals. Always examine the residuals of your chosen model. They should resemble white now. Ise, no discernible patterns, constant variance, normally distributed. A low AIC doesn't guarantee well-behaved residuals. 4. Theoretical soundness and interpretability. While a model might have the lowest AIC, if its parameters are theoretically unsound or difficult to interpret in the context of your domain, it might not be the best choice. Simpler, more interpretable models are often preferred if their AIC is only marginally higher. 5. Computational cost. Grid searching over a wide range of code snippet and code snippet values can be computationally intensive, especially for large datasets. Start with a reasonable range and expand if necessary. 6. Other criteria. While AIC is popular, consider using BIC or HQIC as well, especially if you prioritize parsimony, simpler models. They might lead to slightly different optimal models. By integrating AIC into your modeling procedure, you move beyond subjective graphical analysis, enabling a more systematic, quantitative, and robust approach to identifying suitable ARMA models for your time series data. 6.4.2. Selecting a model using the AIC. In the previous sections, we established the theoretical underpinnings of ARMA processes and the utility of the Akaika Information Criterion, AIC, for model selection. While the autocorrelation function, ACF, and partial autocorrelation function, PACF, plots are invaluable for identifying pure AR, P, or MAQ processes, they often become ambiguous when dealing with mixed ARMA, P, Q models. The characteristic tails-off behavior in both plots for ARMA processes makes visual identification of code snippet and code snippet orders challenging, if not impossible. This section moves beyond visual inspection to a systematic, quantitative approach for selecting the optimal ARMA, P, Q model orders. We will leverage the AIC to compare numerous candidate models and identify the one that best balances goodness of fit with model complexity. This automated procedure is not only more robust, but also essential for practical time series analysis. The challenge of ARMA order identification. Let's first revisit why visual methods fall short for ARMA processes. When a time series exhibits both autoregressive and moving average components, The individual effects tend to blend and obscure the clear cutoff seen in pure AR or MA processes ACF/PACF plots. To illustrate this, let's simulate an ARMA 1 process and examine its ACF and PACF plots. Recall that for an ARMA process, both the ACF and PACF theoretically tail off, decay exponentially or sinusoidal. LY, rather than cut off after a specific lag. Download the code on one patch code Substack. This initial code block sets up our environment, imports necessary libraries, and simulates a synthetic ARMA 1 time series. We explicitly define the AR and MA coefficients, code snippet, to create a known process. The code snippet class from code snippet is a convenient way to generate samples from a specified ARMA model. Setting a code snippet ensures that our simulated data is reproducible, which is crucial for debugging and consistent results. Next, we verify the stationarity of our simulated series using the augmented Dickey-Fuller ADF test, a prerequisite for applying ARMA models. Download the code on one patch code Substack. The ADF test output confirms that our simulated ARMA 1 series is stationary. A p-value significantly less than 0.05 usually indicates stationarity. This is important because ARMA models, by definition, are applied to stationary time series. If a series is non-stationary, it typically needs to be differenced first, leading to an ARMA model. Now let's visualize the ACF and PACF plots for our simulated ARMA 1 series. This is where we observe the ambiguity that necessitates a systematic approach. Download the code on one patch code Substack. Upon inspecting the ACF and PACF plots, you'll notice that neither plot exhibits a clear cutoff after a specific lag. Instead, both show a decaying pattern, albeit with some significant spikes at I. Initial lags. This tailing off behavior in both plots is characteristic of mixed ARMA processes, making it difficult to definitively determine code snippet and code snippet by visual inspection alone. For instance, if you only saw these plots, it would be challenging to confidently state that the underlying process is ARMA 1 without prior knowledge. This ambiguity is precisely why we need a more robust, quantitative method for model selection. Devising a systematic model selection procedure. The solution to the ARMA order identification problem lies in a systematic search procedure that leverages information criteria like AIC. The general steps are as follows. 1. Define search space. Specify a reasonable range for the AR order code snippet and MA order code snippet. This range should be chosen based on domain knowledge, prior analysis, or simply starting with a common range, e.g. 0 to 5. 2. Generate combinations. Create all possible unique combinations of code snippet within the defined search space. 3. Iterative model fitting. For each code snippet combination, fit an ARMA, P, Q model to the time series data. Calculate the AIC for the fitted model. Store the code snippet orders along with their corresponding AIC values. 4. Identify optimal model. After fitting all candidate models, sort the results by AIC in ascending order. The model with the lowest AIC is considered the best candidate. 5. Validation. Crucial next step, the model with the lowest AIC is a STR. On candidate, but it's not the final answer. It must undergo further diagnostic checks, particularly residual analysis, to ensure it adequately captures the underlying data patterns and that its assumptions are met. This step is covered in subsequent sections, defining the search space and generating combinations. The first step in our systematic procedure is to define the maximum code snippet and code snippet orders we are willing to consider. This range dictates the number of models we will fit. A larger range means fitting more models, which increases computational time. For our example, we'll consider code snippet and code snippet values ranging from 0 to 3. This creates a code snippet possible combinations, including pure AR, P, pure MA, Q, and mixed ARMA, PQ models. Note that code snippet typically represents a white noise process, no AR or MA components, which can serve as a baseline. We use Python's code snippet function to efficiently generate all ordered pairs code snippet from the specified ranges. Download the code on one PACF Substack. In this code segment, code snippet and code snippet define the potential values for the AR and MA orders, respectively. Code snippet ensures that code snippet and code snippet are inclusive in our search. Code snippet is a highly efficient way to get every possible pair from these two ranges. It returns an iterator, so we convert it to a code snippet for easy inspection. This code snippet now contains all the code snip ET tuples that our model selection function will iterate through. Implementing the automated ARMA model selection function. The core of our systematic approach is a function that automates the process of fitting ARMA models for each code snippet combination, calculating their AIC, and storing the results. We will call this function code snippet. A critical aspect of this function is robust error handling. Time series model fitting, especially with iterative optimization algorithms, can sometimes fail to converge or encounter numerical issues, particularly for certain code snippet combinations or challenging datasets. Using code snippet blocks ensures that our script doesn't crash, but rather skips problematic models and continues processing, providing a more complete set of results. Download the code on one PACF Substack. This code snippet function is the workhorse of our systematic selection. 1. Initialization. It starts by initializing an empty list code snippet to store the code snippet, and AIC for each successfully fitted model. 2. Iteration. The code snippet loop iterates through every combination generated earlier. 3. Model instantiation and fitting. Inside the loop, code snippet creates an ARMA model object for the current code snippet orders. The code snippet method then estimates the model parameters. Code snippet is used to suppress the detailed optimization output for each model, making the console cleaner. 4. AIC extraction. After a successful fit, code snippet provides the ARMA information criterion value. 5. Error handling. Code snippet. This is a crucial best practice. Code snippet. This often occurs when code snippet cannot estimate the model parameters, perhaps due to singularities or issues with the data for a given order. Code snippet. This is a code snippet-specific warning indicating that the optimization algorithm did not fully converge. While a model might still be returned, its parameters might not be optimal, and its AIC might be unreliable. We explicitly code snippet and code snippet at the top to manage these. Code snippet, a general catch-all for any other unforeseen issues. In all error cases, we print a message and append code snippet for the AIC, allowing us to see which models failed without stopping the entire process. 6. Storing and sorting results. Finally, the collected code snippet list is converted into a code snippet, which is then sorted by the code snippet column. This makes it easy to identify the best model, lowest AIC. Now, let's execute this function with our simulated ARMA, 1, data, and the code snippet we prepared. Download the code on one PACF Substack. The output will show a table of all code snippet combinations that were attempted, along with their corresponding AIC values, sorted from lowest to highest. Since we simulated an ARMA 1.1 process, we would ideally expect the ARMA 1.1 model to have the lowest AIC, or perhaps a very close competitor, indicating our SY. Systematic approach correctly identified the underlying process structure. Interpreting the results. The data frame code snippet presents a clear summary of our model selection process. The first row, with the lowest AIC, indicates the model that best balances fit and complexity according to the AIC criterion. For our simulated ARMA 1.1 data, you should observe that code snippet is likely at or near the top of the list with the lowest AIC. This demonstrates the effectiveness of a systematic search using AIC. However, it's also common to see other models, e.g., ARMA 2.1 or ARMA 1.2, with very similar AIC values, especially when the true parameters are small or the series is short. This highlights that AIC is a guide, not an absolute truth. Visualizing the AIC grid enhancement. While the sorted data frame is useful, a heat map can provide a more intuitive visual representation of the AIC values across the code snippet grid, allowing for quick identification of the optimal region. Download the code on OnePatchCode Substack. This code block uses code snippet to reshape our results into a matrix suitable for a heat map. Code snippet then visualizes this matrix with annotations showing the exact AIC values. The code snippet, reversed Vortis color map, makes lower AIC values appear brighter, clearly highlighting the optimal code snippet combination. Models that failed to fit with code snippet AIC will appear as a distinct color or blank depending on code snippet strategy. This heat map offers a powerful visual summary, quickly showing not just the single best model, but also the landscape of AIC values. You can easily spot if there are multiple models with very similar AICs, suggesting that further diagnostics are needed to choose between them. Considerations and best practices. Computational cost. Be mindful that as the code snippet and code snippet values increase, the number of models to fit grows quadratically. For instance, code snippet means code snippet models. For larger data sets or higher order ranges, this can become computationally intensive. Consider setting reasonable maximums based on domain knowledge or initial ACF/PACF insights. Other information criteria. While AIC is widely used, other criteria exist. Bayesian information criterion, BIC, similar to AIC, but imposes a larger penalty for the number of parameters. It tends to select simpler models, lower code snippet and code snippet, than AIC, especially for larger datasets. Hannon-Quinn information criterion, HQIC, falls between AIC and BIC in terms of penalty. The choice between AIC, BC, and HQIC often depends on specific goals. AIC aims to select the model that best predicts future observations, while BIC aims to select the true model among the candidates. AIC and number of parameters. Code snippet. The AIC formula is $AIC equals 2K, 2\ln, \addl, $, where code snippet is the number of estimated parameters and $hat $L is the maximum likelihood of the model. 4. An ARMA PQ model. Code snippet typically includes code snippet AR coefficients, code snippet MA coefficients, and a constant term, intercept. So, code snippet. If the model also estimates a mean, or if it's differenced, ARMA, code snippet can vary. Code snippet automatically handles the correct code snippet for its AIC calculation. Beyond AIC, residual analysis. Identifying the model with the lowest AIC is just the first step. The chosen model must undergo rigorous residual analysis to confirm its adequacy. This includes checking if the residuals are white noise, no remaining autocorrelation, checked with ACF/PCF of residuals and Lejeune box test. Normally distributed, checked with histogram, QQ plot, and statistical tests like Shapiro-Wilk. Homoscedastic, constant variance. If residual assumptions are violated, the model is likely misspecified, and further investigation, e.g., trying different orders, including exogenous variables, or considering nonlinear models, is necessary. This will be covered in detail in the next section. 6.4.3 Programmatic ARMA Model Selection with AIC. Identifying the optimal orders code snippet and code snippet for an ARMA PQ model is a crucial step in time series analysis. While tools like the autocorrelation function, ACF, and partial autocorrelation function, PACF, plots provide initial insights, they can be ambiguous, especially for mixed ARMA processes. To overcome this, we employ a systematic, quantitative approach, a grid search combined with the archaic information criterion, AIC. This method allows us to programmatically evaluate a range of candidate ARMA models and select the one that best balances goodness of fit with model complexity. The need for automated model selection. In earlier sections, we discussed how ARMA models capture the linear dependencies in a stationary time series. We also noted the challenges in precisely identifying code snippet and code snippet orders using visual inspection of ACF and PACF plots. For instance, an AR-1 process might show a decaying PACF and a sharp cutoff in ACF, but an ARMA-1 process could exhibit decaying patterns in both, making visual identification difficult. A grid search provides a robust solution. Instead of guessing, we define a reasonable range for code snippet and code snippet, e.g., code snippet from 0 to 5, code snippet from 0 to 5, and then systematically fit an ARMA model for every combination within that range. For each fitted model, we calculate its AIC score. The model with the lowest AIC is then C. Considered the most parsimonious, simplest model that provides the best fit to the data among those tested. This automation is essential for reproducibility and efficiency, particularly with large datasets or when exploring many model configurations. Understanding code snippet for ARMA. The code snippet library in Python is a powerful tool for time series analysis. For fitting ARMA models, we leverage the code snippet class, code snippet. While its name suggests suitability for seasonal autoregressive integrated moving average with exogenous regressors, SARMAX, it is a highly general model that can be simplified to fit basic ARMA models. To fit an ARMA PQ model using code snippet, we need to correctly specify its parameters. Code snippet. This is your time series data, typically a pandas series. It must be stationary for an ARMA model. Code snippet. This tuple defines the non-seasonal components. Code snippet. The order of the autoregressive AR part. Code snippet. The order of differencing integrated part. For a pure ARMA model, the data is assumed to be already stationary, so we set code snippet. If code snippet, you would be fitting an ARMA model. Code snippet. The order of the moving average MA part. Code snippet. This tuple defines the seasonal components. For a non-seasonal ARMA model, all seasonal orders are set to 0. Code snippet. Code snippet. This parameter controls whether a constant, intercept, term is included in the model. Code snippet. Constant includes a constant term. This is generally recommended unless you have a strong reason to believe the series has a 0 mean. Code snippet. No constant excludes a constant term. Code snippet. This is a critical parameter for code snippet when fitting ARMA. By default, code snippet might attempt to automatically difference the data if it detects non-stationarity. Setting code snippet explicitly tells the model not to perform any automatic differencing, ensuring you are fitting a pure ARMA PQ model on your already stationary code snippet data. Constructing the code snippet function. We will now build a Python function, code snippet, that encapsulates the grid search logic. This function will take your stationary time series data and a list of code snippet order combinations to test. It will return a pandas data frame containing the AIC for each tested model, sorted from lowest to highest. 1. Setup and imports. First, we need to import the necessary libraries. Code snippet and code snippet are standard for data manipulation. Code snippet is from code snippet. Code snippet will help us generate code snippet combinations. Code snippet provides a convenient progress bar for long-running loops, especially useful in Jupyter environments. We also include code snippet to suppress verbose output that might clutter our results. Download the code on one PageCode Substack. These lines set up our environment. Code snippet is particularly helpful as fitting many models can. Take time, and a progress bar gives visual feedback. Suppressing warnings is a practical step for automated scripts. However, in a diagnostic phase, you might want to re-enable warnings to understand specific model fitting issues. 2. Function definition and parameters. Next, we define the code snippet function. It will take code snippet, our time series, and code snippet, the code snippet combinations as input. Download the code on one PageCode Substack. The function signature includes type hints, code snippet, code snippet, code snippet, for clarity and maintainability. indicating the expected input and output types. The code snippet list will temporarily hold the code snippet order and AIC for each successful model fit. 3. Iterating through orders with error handling. The core of the function involves iterating through each code snippet combination, attempting to fit in code snippet model, and then extracting its AIC. Model fitting can sometimes fail due to issues like non-convergence, singular matrices, or invalid parameter combinations, e.g., if the time series is too short for the specified orders. To make our function robust, we wrap the fitting process in a code snippet block. Download the code on one patch code substack. Inside the loop, code snippet wraps the iteration, displaying a progress bar. The code snippet constructor is called with code snippet to specify ARMA, P, Q. The code snippet is crucial. Code snippet explicitly states no seasonality. Code snip, T adds an intercept term. The number of parameters code snippet in the AIC formula, code snippet, for an ARMA, P, Q model with a constant is typically code snippet for coefficients and a constant, +1 for the variance of the residuals. Code snippet correctly accounts for these internally. If code snippet, no constant, were chosen, code snippet would be code snippet plus the variance parameter. Code snippet is vital to ensure you're fitting an ARMA model on your already stationary series, preventing code snippet from applying internal differencing. Code snippet performs the parameter estimation. Code snippet keeps the output clean by suppressing the iteration log during the optimization process. Code snippet retrieves the calculated AIC value. If an error occurs, the code snippet block catches it. A warning is printed, and code snippet is recorded for the AIC to indicate a failed fit, allowing the process to continue without crashing. 4. Processing and returning results. After the loop completes, the code snippet list, containing tuples of code snippet orders and their corresponding AICs, is converted into a pandas data frame. This data frame is then sorted by the AIC column in ascending order, making it easy to identify the best model, lowest AIC. Download the code on one patch code substack. Code snippet arranges the models from best, lowest AIC to worst. Code snippet cleans up the data frame's index after sorting, generating the search space for code snippet O. Writers. Before we can use our code snippet function, we need a list of code snippet combinations to test. The code snippet function is perfect for this, generating all Cartesian products of input iterables. Download the code on one patch code substack. Here, we define code snippet and code snippet to set the boundaries of our search. Code snippet efficiently creates all code snippet pairs, including code snippet, which represents a white noise process. While code snippet might not be considered a model in the traditional sense, including it can sometimes provide a baseline AIC against which other models are compared. Applying code snippet to data. Now, let's demonstrate the code snippet function first with a simulated dataset, and then with our real-world bandwidth usage data. 1. Simulated data example. We'll start by generating a simple ARMA 1 process to see if our function correctly identifies the true orders. Download the code on one patch code substack. This code creates an ARMA 1 series using specified AR and MA coefficients. This simulated data will act as a controlled environment to test our code snippet function. Download the code on one patch code substack. After running the code snippet function, we inspect the top results. Ideally, the code snippet order should appear with the lowest AIC, indicating that our function successfully identified the true underlying process. 2. Identifying and fitting the best model. Once the grid search is complete, the best model is simply the first row of our sorted code snippet. We can then use these optimal orders to fit the final model and inspect its full summary, which provides detailed statistics and diagnostics. Download the code on one patch code substack. The code snippet output is rich with information, including coefficients, the estimated values for the AR and MA parameters, standard errors, and p-values. Indicate the statistical significance of the coefficients. AIC, BC, HQC. Other information criteria, we focused on AIC. Ljungbox test, a diagnostic test for the residuals. We want high p-values, e.g., greater than 0.05, indicating that the residuals are white noise, meaning the model has captured all the relevant information. Jarkbera test, test for normality of residuals. Heteroscedasticity test, checks for constant variance of residuals. Analyzing this summary is a crucial next step after model selection, as it validates whether the chosen model is truly appropriate and if its assumptions are met. 3. Visualizing AIC landscape. To gain a deeper understanding of how AIC values vary across the code snippet grid, a heat map visualization can be incredibly insightful. It allows you to visually identify the minimum AIC and observe trends or local minima. Download the code on one patch code Substack. This code transforms our linear code snippet into a pivot table, which is the required format for a heat map with code snippet orders on one axis and code snippet orders on the other. Download the code on one patch code Substack. The heat map visually represents the AIC values. The code snippet color map typically shows lower values, better AIC, in brighter colors. You can easily spot the code snippet cell, or closest to it due to random noise, with the lowest AIC, confirming the programmatic selection. This visualization helps in understanding the sensitivity of AIC to changes in code snippet and code snippet. Applying to real-world bandwidth usage data. Let's now apply our code snippet function to the bandwidth usage dataset that we've been working with in previous sections. Recall that for ARMA modeling, the time series must be stationary. If the original bandwidth usage data was non-stationary, e.g., showed a trend, we would first apply differencing to make it stationary. For this example, we will assume a first difference series is used. Download the code on one patch code Substack. This block loads the code snippet file, sets the date column as the index, and converts the usage column into a Panda series. Crucially, it then applies a first difference and drops the resulting code snippet to achieve stationarity, which is a prerequisite for ARMA modeling. Download the code on one patch code Substack. This final application demonstrates how to use the code snippet function on real-world data. It provides the optimal code snippet orders based on AIC and then displays the comprehensive summary of the best-fitting model, enabling further diagnostic checks. Consideration: NS and best practices. Computational cost. A grid search can be computationally intensive, especially if code snippet and code snippet are large. The number of models to fit grows quadratically with the order ranges. For very large search spaces or high-frequency data, alternatives like the code snippet library's code snippet function, which uses more advanced search strategies, or other machine learning approaches might be more efficient. AIC's relative nature. Remember that AIC is a relative measure. It helps identify the best model among those tested. It does not guarantee that the best model is a good model in an absolute sense, or that it will perform well in forecasting. Always follow up model selection with thorough diagnostic checks, e.g., residual analysis and out-of-sample forecasting evaluation. Stationarity. The code snippet function assumes the input code snippet series is stationary. If your raw data is non-stationary, e.g., has a trend or seasonality, you must apply appropriate differencing or seasonal differencing before passing it to this function. For instance, if a series requires first differencing, you would fit an ARMA P1Q model, which is effectively an ARMA PQ model on the different series. Model validation beyond AIC. While AIC is excellent for initial model identification, it is not the sole criterion. Always perform residual analysis, checking for white noise, normality, homoscedasticity of errors, and backtesting, evaluating forecasts. Testing performance on unseen data to fully validate your chosen model. Interpretation of code snippet in AIC. For an ARMA PQ model, the number of estimated parameters code snippet for the AIC calculation usually includes code snippet AR coefficients, code snippet MA coefficients, and one parameter for the constant, if code snippet, +1 for the variance of the residuals. Code snippet handles this correctly internally. 6.4.3 Understanding residual analysis. After gathering data, ensuring stationarity, and employing criteria like the ACF Information Criterion, AIC, to select candidate ARMA model orders, the final and arguably most crucial step in validating a time series model is residual analysis. While AIC helps us choose the relatively best model among a set of candidates by balancing fit and complexity, residual analysis evaluates the absolute quality of the chosen model. It tells us whether the model has successfully captured all systematic patterns in the data, leaving only random, unpredictable noise. The concept of white noise residuals. A well-specified time series model should transform the original, complex time series into a simpler, uncorrelated series of errors, known as residuals. Ideally, these residuals should resemble white noise. White noise is a fundamental concept in time series analysis, characterized by 3 key properties. 1. Zero mean. The average of the residuals should be close to 0, indicating no systematic over or under prediction. 2. Constant variance. Homoscedasticity, the spread of the residuals, should be consistent over time, implying that the model's predictive accuracy doesn't vary significantly. 3. No autocorrelation. Crucially, there should be no discernible pattern or correlation between residuals at different time lags. If autocorrelation exists, it means there's still systematic information in the data that the model failed to capture, render, i.e. it incomplete or incorrectly specified. 4. Normality, often desired, but not always strict for many statistical inference procedures, e.g., confidence intervals for forecasts. Residuals are also assumed to be normally distributed. While not strictly required for a model to be valid, non-normal residuals can indicate issues with the model's assumptions or the presence of outliers. If residuals deviate significantly from these white noise properties, it suggests that the model is inadequate. It implies that uncaptured patterns, biases, or incorrect distributional assumptions persist, making the model unreliable for forecasting or inference. Tools for residual analysis. To assess whether residuals resemble white noise, we primarily use 2 diagnostic tools: the quantile QQ plot for normality and the Ljungbox test for autocorrelation. Assessing normality with QQ plots. A quantile QQ plot is a graphical tool used to assess if a set of data, in our case, model residuals, follows a specific theoretical distribution, most commonly the normal distribution. It plots the quantiles of the observed data against the quantiles of the theoretical distribution. If the residuals are indeed normally distributed, the points on the QQ plot will roughly fall along a straight 45-degree line. Any significant deviation from this line indicates a departure from normality. Let's demonstrate this with a simulated ARMA 1-1 process and then fit a correct model to it. First, we'll generate some synthetic data that follows an ARMA 1-1 process. This allows us to know the true underlying process and verify if our model correctly identifies it. Download the code on one patch code Substack. This code snippet generates a synthetic time series that behaves like an ARMA 1-1 process. We define the autoregressive AR and moving average MA coefficients, then use code snippet to create the series. Plotting it helps us visualize the generated data. Next, we'll fit an ARMA 1-1 model to this simulated data and extract its residuals. Download the code on one patch code Substack. Here, we fit the code snippet model with code snippet to our simulated data. The code snippet order corresponds to an ARMA 1-1 model because the middle component code snippet indicates no differencing. We then print the code snippet to review the model's parameters and fit statistics, including AIC, though not the focus here. Finally, we extract and plot the residuals. Ideally, this plot should look like random noise centered around 0. Now, let's generate the QQ plot for these residuals. Download the code on one patch code Substack. The code snippet function from code snippet is used here. The code snippet argument adds a standardized line, a line through the first and third quartiles, which helps in visually assessing normality. For our correctly specified ARMA 1 model, the QQ plot should show points closely hugging the straight line, indicating that the residuals are approximately normally distributed. Interpreting QQ plot deviations. S-shape suggests that the data has heavier tails than a normal distribution, i.e., more extreme values than expected. Curvature at ends indicates skewness. If the points curve upwards at the upper end and downwards at the lower end, it may suggest a right-skewed distribution. The opposite curvature suggests left-skewed. Flatness/steepness can indicate issues with variance or incorrect scaling, but often also points to non-normality. If the QQ plot shows significant deviations, it suggests that the assumption of normally distributed residuals is violated. This might not invalidate the model entirely for forecasting, but could impact the validity of confidence intervals for forecasts or certain statistical tests. Checking for autocorrelation with the Ljung box test. The Ljung box test is a formal statistical test used to check for the presence of autocorrelation in the residuals. It tests the null hypothesis that the residuals are independently distributed, i.e., there is no autocorrelation up to a specified number of lags. Null hypothesis, $H0, the residuals are independently distributed, i.e., resemble white noise. Alternative hypothesis, $H1, the residuals are not independently distributed, i.e., some autocorrelation exists. The test calculates a Q statistic based on the squared autocorrelations of the residuals. A small p-value, typically less than 0.05, leads us to reject T. A null hypothesis, indicating that significant autocorrelation is present in the residuals. Conversely, a large p-value, greater than 0.05, suggests that we cannot reject the null hypothesis, implying that the residuals are indeed white noise. Let's apply the Ljung box test to our ARMA 1 model residuals. Download the code on OnePageCode Substack. The code snippet function performs the test. The code snippet argument specifies the maximum lags for which to compute the test statistic. It's common to check several lags to ensure no patterns are missed. The code snippet argument is crucial when testing residuals from a fitted model. It accounts for the degrees of freedom lost due to estimating the model parameters. For an ARMA PQ model, code snippet should be code snippet. In our ARMA 1 case, code snippet and code snippet, so code snippet. If this parameter is omitted or incorrect, the p-values might be misleadingly low. For our correctly specified ARMA 1 model, we expect the p-values for all lags to be high, e.g., much greater than 0.05, indicating no significant autocorrelation in the residuals. This confirms that our model has successfully captured the underlying patterns. The iterative modeling procedure with residual analysis. Residual analysis is the final gatekeeper in our iterative time series modeling process. Here's how it fits into the broader procedure. 1. Data preparation. Gather data, clean, and visualize. 2. Stationarity check. Test for stat-iona. Write and apply differencing if necessary, determining D in ARMA, P, DQ. 3. Model identification. Initially use ACF and PACF plots or more advanced methods to get initial guesses for P and Q. 4. Model selection. AIC/BC fit a range of ARMA, P, Q models with a determined D and select the model with the lowest AIC or BIC. This provides the relatively best model. 5. Residual analysis, absolute quality check. Extract residuals from the chosen model. Generate a QQ plot to check for normality. Perform the Ljung box test to check for autocorrelation. 6. Decision point. If residuals resemble white noise, QQ plot is straight, Ljung box p-values are high, the model is statistically sound and suitable for forecasting. If residuals do not resemble white noise, QQ plot deviates, Ljung box p-values are low, the model is inadequate. This is a critical feedback loop, indicating that the model has not captured all the information in the series. If the model fails the residual analysis, we must return to step 3 or 4. Strategies for selecting new P-Q combinations include trying the next best AIC models. If your initial model was the absolute lowest AIC, check the models that had the second or third lowest AIC values. Sometimes, a slightly higher AIC model might pass residual checks better. Exploring adjacent orders. Try code snippet and code snippet values that are close to the failed model's orders. E.g., if ARMA 1.1 failed, try ARMA 1.2, ARMA 2.1, ARMA 2.2. Revisiting differencing. If strong autocorrelation persists, it might indicate that the series was not sufficiently differenced or perhaps over-differenced. Considering seasonality. If the data has seasonal patterns, a seasonal ARMA model might be more appropriate. Looking for structural breaks/outliers. Sometimes, unusual events or data errors can cause residuals to deviate. Counterexample, when residual analysis fails. To illustrate what bad residual analysis looks like, let's intentionally fit an underspecified model to our simulated ARMA 1.1 data. We'll try fitting a simple AR-1 model, ARMA 1.0, to data that we know is actually ARMA 1.1. This means we're missing the MA1 component. Download the code on one patch code substack. Notice how the code snippet is in code snippet model, meaning it only accounts for an AR-1 component. Since the true data is ARMA 1.1, we expect this model to fail to capture the MA1 dependency, leaving it in the residuals. The plot of code snippet might already show some patterns, indicating non-randomness. Now, let's run the QQ plot and Ljungbox test on these underspecified residuals. Download the code on one patch code substack. For the underfit model, you would typically observe QQ plot, significant deviation from the straight line, possibly an S-shape or other curvature, indicating non-normality. This can happen if the model fails to account for certain distributional aspects of the data. Ljungbox tests. The p-values for most, or all, lags will likely be very low, e.g., close to 0, much less than 0.05. This strongly indicates that significant autocorrelation remains in the residuals, meaning the model has not captured all the systematic patterns in the data. When such results appear, it is a clear signal to go back to the model selection phase, perhaps considering higher orders for code snippet, or re-evaluating the differencing order code snippet. This iterative refinement is a cornerstone of robust time series modeling. 6.4.4 Performing Residual Analysis. After selecting a promising ARMA PQ model using criteria like AIC, the next critical step in our general modeling procedure is to validate the chosen model. This validation is primarily performed through residual analysis. Residuals are the differences between the actual observed values and the values predicted by our fitted model. In essence, they represent the unexplained portion of the time series after the model has captured its underlying patterns. The importance of white noise residuals. For a time series model to be considered well-specified and robust, its residuals should ideally resemble white noise. A white noise process is a sequence of random variables that are 1, 0 mean. The average of the residuals should be close to 0, indicating no systematic bias in the model's predictions. 2. Constant variance. Homoscedasticity, the spread of the residuals, should be consistent over time, implying that the model's predictive power does not vary significantly across the series. 3. No autocorrelation. This is arguably the most crucial property. There should be no discernible patterns or dependencies, autocorrelation, left in the residuals. If autocorrelation exists, it means our model has failed to capture all the systematic information in the original time series, and that information is still present in the errors. This implies that a better model could potentially be found. For normally distributed, optional but desirable W. While not strictly required for all time series models, Assuming normally distributed errors often simplifies statistical inference, e.g., constructing confidence intervals for forecasts. Many statistical tests and confidence intervals for model parameters rely on this assumption. If the residuals exhibit these white noise properties, it suggests that our model has successfully captured all the significant linear dependencies in the data, and what remains is purely random noise. If they do not, it signals that the model is misspecified and we need to revisit earlier steps, such as exploring different AR and MA orders, considering differencing, or even evaluating alternative model classes. Methods for residual analysis. We can assess the white noise properties of residuals using both qualitative, visual, and quantitative statistical test methods. Qualitative analysis. Visual inspection of residual plots. Visual inspection provides an intuitive understanding of residual behavior. We typically look at residuals over time plot to check for trends, patterns, or changes in variance. Histogram and density plot to assess the distribution of residuals, ideally looking for a bell-shaped curve centered at 0. Normal QQ plot to formally check for normality. Autocorrelation function, ACF, of residuals to identify any remaining autocorrelation. Quantitative analysis, statistical tests. While visual inspection is helpful, it can be subjective. Statistical tests provide objective criteria. Ljungbox test, the primary statistical test used to check for the absence of autocorrelation in the residuals. Let's now apply these concepts using Python's code snippet library. Practical implementation with code snippet. For this demonstration, we'll simulate an ARMA 1.1 process and then fit an ARMA 1.1 model to it. This allows us to work with a ground truth where we know the underlying process should theoretically be well captured by the chosen model. First, we need to import the necessary libraries and simulate our data. Download the code on OnePageCode Substack. Here, we import code snippet for numerical operations, code snippet for plotting, and various modules from code snippet. Code snippet will help us create our synthetic time series data. Code snippet is the class we'll use to fit our ARMA model. Code snippet is for normal quantile-quantile plots, and code snippet performs the Ljungbox test. We also set a random seed to ensure our simulated data is consistent every time the code is run. Simulating ARMA 1.1 data. Let's generate 200 data points from an ARMA 1.1 process. An ARMA 1.1 process has one autoregressive AR term and one moving average MA term. Download the code on OnePageCode Substack. In this code block, code snippet defines the autoregressive part. Here, a coefficient of 0.7 for the first lag, meaning code snippet depends on code snippet. The code snippet defined the moving average part. Here, a coefficient of 0.44. The first lag of the error term, meaning code snippet depends on code snippet. The code snippet function then uses these coefficients to produce a time series of code snippet length. We then visualize this simulated data to get a sense of its behavior, fitting the ARMA model and extracting residuals. Now, we'll fit an ARMA 1.1 model to our simulated data using code snippet. The code snippet class in code snippet is highly versatile and can handle ARMA, ARIMA, SARIMA, and SARMAX models. For a pure ARMA PQ model, we specify the code snippet parameter as code snippet, where the middle code snippet indicates no differencing, i=0 for integrated. We also set code snippet to ensure that the model is treated as a pure ARMA process without any implicit differencing. Download the code on OnePageCode Substack. After fitting the model using code snippet, we access the code snippet attribute of the code snippet object. This attribute contains the time series of the prediction errors. We print the first few residuals to see their values. Visual analysis of residuals. With the residuals extracted, we can now proceed with their visual assessment. Standalone QQ plot for normality. A quantile-quantile QQ plot is a graphical tool used to assess if a dataset follows a particular distribution, in our case, a normal distribution. It plots the quantiles of our residuals against the quantiles of a theoretical normal distribution. Download the code on one patch code Substack. The code SN IPIT function from code snippet is used here. The code snippet parameter is crucial. It draws a 45-degree reference line. If the residuals are perfectly normally distributed, their points on the plot should fall approximately along this 45-degree line. Deviations from this line, especially at the tails, indicate departures from normality. For instance, points curving above the line at the top and below at the bottom suggest heavy tails, more extreme values than a normal distribution, while an S shape might indicate skewness. Comprehensive diagnostic plots with code snippet. Code snippet provides a convenient method, code snippet, on the fitted model object that generates a panel of 4 essential diagnostic plots for residuals. This gives a quick and comprehensive overview. Download the code on one patch code Substack. The code snippet method returns a matplotlib figure object, which we can then customize, for example, by adding a main title. Let's break down the interpretation of each of the 4 plots it generates. 1. Standardized residuals, top left. This plot shows the residuals over time, often standardized, divided by their standard deviation, for easier comparison. Interpretation. We look for any patterns, trends, or changes in variance. Ideally, residuals should fluctuate randomly around 0 without any discernible structure. Any systematic pattern, e.g., increasing variance over time, cyclical behavior, indicates that the model has not captured all the in-format ion in the series and needs refinement. For our ARMA 1.1 model, we expect random noise. 2. Histogram plus estimated density, top right. This is a histogram of the residuals, overlaid with a kernel density estimate, KD, and a normal distribution curve. Interpretation. This plot helps assess the distribution of residuals. We want the histogram bars to approximate a bell curve and the KD line to closely follow the normal distribution curve. The title often includes the Jark-Barra test statistic and its p-value, which formally tests for normality, null hypothesis. Data is normally distributed. A low p-value, e.g., less than 0.05, would suggest non-normality. For our simulated ARMA 1.1, with normally distributed errors, we expect a good fit to the normal curve. 3. Normal QQ, bottom left. This is identical to the code snippet we generated independently earlier. Interpretation. As discussed, points should lie close to the 45-degree line, indicating that the residuals quantiles match those of a theoretical normal distribution. Deviations suggest non-normality. 4. Parallelogram, ACF of residuals, bottom right. This plot shows the autocorrelation function, ACF, of the residuals for various lags. The shaded area represents the confidence interval, typically 95%. Interpretation. For white noise residuals, we expect no significant autocorrelations at any lag. This means all the bars should fall within the shaded confidence interval. If any bar extends beyond the confidence interval, it indicates significant autocorrelation at that lag, meaning there's still predictable information left in the residuals that the model didn't capture. For our well-fitted ARMA 1.1 model, we anticipate no significant spikes. Quantitative analysis, Ljung box test. While visual inspection is valuable, it's subjective. The Ljung box test provides a formal statistical test to check for the absence of autocorrelation in the residuals. Null hypothesis, $H0, the residuals are independently distributed, i.e., there is no autocorrelation up to a specified lag. Alternative hypothesis, $H1, the residuals are not independently distributed, i.e., there is significant autocorrelation. The test calculates a Q statistic based on the squared autocorrelations of the residuals. If the Q statistic is large enough, we reject the null hypothesis, concluding that there is significant autocorrelation. We typically look at the p-value associated with the test statistic. Download the code on one patch code Substack. The code snippet function returns a data frame containing the Ljung box test statistic, code snippet, and the corresponding p-value, code snippet, for each specified lag. We are primarily interested in the p-values. Interpreting the Ljungbox p-values. If the p-value for a given lag is greater than a chosen significance level, e.g., 0.05, we fail to reject the null hypothesis. This indicates that there is no significant autocorrelation at that lag. If the p-value is less than the significance level, we reject the null hypothesis, suggesting that there is significant autocorrelation at that lag. For a well-fitted model, we expect all p-values across the tested lags to be greater than our chosen significance level, e.g., 0.05, indicating that the residuals are indeed uncorrelated. Let's add a programmatic check to confirm this. Download the code on one patch code Substack. This programmatic check provides an immediate summary of the test results, making it easier to determine if the residuals pass the autocorrelation test. What if residual analysis fails? If the residual analysis indicates that your model's residuals are not white noise, e.g., significant spikes in the ACF, non-normal distribution, or patterns in the residuals over time, it implies that your chosen model has not captured all the relevant information in the data. This is a critical signal that your model is likely misspecified and its forecasts may be biased or inefficient. Here are concrete steps to take when residual analysis fails. 1. Reevaluate AR and MA orders, PQ. Go back to the ACF and PACF plots of the original or differenced series. Are there other orders that look plausible? Expand your AIC/BC search grid. Perhaps the optimal model was just outside your initial search range. Consider alternative combinations of code snippet and code snippet that might better capture the autocorrelation structure. 2. Consider differencing if not already done. If the residuals show a trend or persistent autocorrelation, the original series might not have been stationary enough. Apply additional differencing code snippet in ARMA and reevaluate. 3. Account for seasonality. If the residuals show patterns at seasonal lags, e.g., every 12 months for monthly data, you might need to incorporate seasonal components into your model, e.g., using ARMA. 4. Check for outliers or structural breaks. Sudden spikes or shifts in the residuals could indicate outliers or structural breaks in the original data that the model cannot explain. These might need to be handled separately, e.g., using dummy variables or intervention analysis. 5. Consider other model classes. If the variance of the residuals is not constant, heteroscedasticity, an ARMA/ARMA model might not be sufficient. You might need to explore GRCH, generalized autoregressive conditional heteroscedasticity, models which specifically model changing variance. If the relationship is nonlinear, a more advanced nonlinear time series model might be required. 6. Re-examine data transformations. If the residuals are highly skewed or non-normal, consider applying transformations, e.g., log transformation, Box-Cox transformation, to the original data, which can sometimes stabilize variance and improve normality. Demonstrating a failed residual analysis. To illustrate what a bad residual analysis looks like, let's fit a clearly suboptimal model, like an ARMA00, which is just white noise, meaning we assume no AR or MA components, to our simulated ARMA1 data. Download the code on one patch code Substack. By comparing the diagnostic plots and Ljungbox test results from the well-fitted ARMA1 model with those from the suboptimal ARMA00 model, you can clearly see the differences. The suboptimal model's residual ACF plot will show significant spikes, bars outside the blue shaded area, indicating uncaptured autocorrelation. The Ljungbox p-values for the suboptimal model will be very low, e.g., close to 0, for many lags, leading to the rejection of the null hypothesis of no autocorrelation. The standardized residuals plot might show patterns, and the QQ plot might deviate significantly from the 45-degree line, although the primary failure for a time series model is usually uncaptured autocorrelation. This stark contrast highlights the importance of thorough residual analysis in guiding the iterative process of time series model building. A model is only as good as its residuals. If they're not white noise, your model is not yet fully capturing the story told by your data. This section brings together all the concepts and techniques learned so far, from data preparation and stationarity testing to automated model selection and rigorous residual analysis, into a comprehensive end-to-end time series modeling procedure. We will apply this general procedure to a real-world dataset, hourly bandwidth usage. This practical application demonstrates how to systematically build and validate a robust ARMA model for forecasting. 1. Loading and initial inspection of bandwidth data. Our first step in any time series analysis is to load the data and perform an initial visual inspection. This helps us understand the data structure, identify obvious trends or seasonality, and check for any immediate issues. We'll be working with a dataset named Code Snippet, which contains hourly bandwidth usage measurements. Download the code on one patch code Substack. The output of Code Snippet and Code Snippet confirms that we have a Code Snippet column and a Code Snippet column. The Code Snippet column is currently in Code Snippet type, which needs to be converted to a datetime format for proper time series handling. The Code Snippet column is already a Code Snippet, which is suitable for numerical analysis. Next, we convert the Code Snippet column to datetime objects and set it as the data frame index. This is a crucial step for Code Snippet to recognize the time series nature of the data, enabling time-based indexing and resampling. Download the code on one patch code Stack. With the data loaded and properly indexed, we can now visualize the raw time series. This plot will immediately reveal prominent features like trends, seasonality, or irregular patterns. Download the code on one patch code Substack. The plot clearly shows a strong upward trend, indicating that bandwidth usage generally increases over time. There's also a noticeable repeating pattern, suggesting daily or weekly seasonality. This visual inspection confirms our initial suspicion that the series is non-stationary, as its statistical properties, like the mean, change over time. 2. Assessing and achieving stationarity. As discussed in previous sections, ARMA models require the time series data to be stationary. A stationary series has constant statistical properties over time, such as mean, variance, and autocorrelation. Our visual inspection of the raw bandwidth usage data strongly suggests it is non-stationary due to the clear upward trend. To formally test for stationarity, we use the augmented Dickey-Fuller ADF test. 2.1 Performing the augmented Dickey-Fuller ADF test. The ADF test is a statistical hypothesis test that determines if a unit root is present in a time series. The presence of a unit root implies non-stationarity. Null hypothesis: H0 the time series has a unit root, i.e., it is non-stationary. Alternative hypothesis: H1 the time series does not have a unit root, i.e., it is stationary. We look for a small p-value, typically less than 0.05 t. Reject the null hypothesis and conclude that the series is stationary. Download the code on one patch code Substack. As expected, the ADF test on the raw code snippet data yields a high p-value, likely much greater than 0.05, confirming that the series is non-stationary. This is consistent with the visible trend in the plot. 2.2 Applying first-order differencing. To achieve stationarity, we apply differencing. First-order differencing calculates the difference between consecutive observations. This often helps remove trends and can also mitigate some forms of seasonality. The code snippet function is ideal for this. Note that differencing will result in one fewer data point than the original series. Download the code on one patch code Substack. The plot of the difference series now appears to fluctuate around a constant mean, 0, in this case, and the strong upward trend has been removed. This visual assessment suggests that the series is now stationary. 2.3 Rechecking stationarity of difference data. We must formally confirm the stationarity of the difference series using the ADF test again. Download the code on one patch code Substack. The ADF test on the difference data should now show a very low p-value, e.g., less than 0.05. allowing us to reject the null hypothesis and conclude that the difference series is stationary. This confirms that first-order differencing was effective in making the series suitable for ARMA modeling. 3. Data preparation. Train test. Split. Before fitting any models, it's crucial to split our stationary time series data into training and testing sets. The training set will be used to fit the model, and the testing set will be used to evaluate its performance on unseen data. 4 time series. This split must preserve the temporal order. We train on an earlier period and test on a later period. We'll use the last 168 observations, equivalent to 1 week of hourly data, for the test set and the rest for training. Download the code on one patch code Substack. The plot visually confirms our train test split, showing the training data followed by the testing data. This setup ensures that our model evaluation is realistic, as it's tested on future, unseen data. 4. Automated ARMA model selection. Now that our data is stationary and split, we can proceed with selecting the optimal ARMA model orders, P, Q. We'll reuse the code snippet function defined in the previous section, 6.4.2. This function systematically iterates through a range of code snippet combinations, fits code snippet models, and records their AIC values. Recap the code snippet function. The code snippet function is designed for automated model selection. It takes the training data and ranges for code snippet and code snippet as input. For each combination, it attempts to fit a code snippet model. A crucial aspect of this function is its internal code snippet block. This block is essential because some code snippet combinations might lead to convergence issues or errors during model fitting, especially with complex real-world data or when the model orders are too high for the given data. The code snippet block gracefully handles these errors, preventing the entire optimization process from crashing, and instead records code snippet for AIC in such cases, allowing the search to continue. Determining the search range for code snippet and code snippet. The choice of code snippet and code snippet ranges, e.g. 0 to 3 for both, is often a balance between finding a good model and computational feasibility. While arbitrary in a strict sense, initial guidance can come from the autocorrelation function, ACF, and partial autocorrelation function, PACF, plots of the different series. ACF for MA order code snippet. A sharp cutoff in the ACF after code snippet lags suggests an MA Q process. PACF for AR order code snippet. A sharp cutoff in the PACF after code snippet lags suggests an AR P process. For this dataset, a range of 0 to 3 for both code snippet and code snippet is a reasonable starting point. However, be mindful of computational cost. Increasing the range significantly, e.g. to 0 to 5, means fitting code snippet models. For ranges 0 to 3, this means code snippet models, which is manageable. For 0 to 5, it would be code snippet models, and so on. The computational complexity grows quadratically with the range. Download the code on one patch code Substack. The code snippet shows the AIC values for each code snippet com. By nation, sorted in ascending order. The model with the lowest AIC is generally preferred as it represents the best trade-off between model fit and complexity. Programmatically selecting the best model. While we can visually identify the best model from the printed code snippet, it's good practice to programmatically select it, especially for larger search spaces. Download the code on one patch code Substack. In many cases, as seen in the output, several models might have very similar AIC values. For example, code snippet, and code snippet might have AICs that are very close. When AIC values are highly similar, it suggests that multiple model structures provide a comparably good fit to the data. In such scenarios, consider these tie-breaking criteria. 1. Parsimony. Choose the simpler model, fewer parameters, i.e., smaller code snippet and code snippet, if the AIC difference is negligible. A simpler model is often more stable and easier to interpret. 2. Theoretical justification. If domain knowledge suggests a certain order and its AIC is competitive, it might be preferred. 3. Residual analysis. If multiple models have similar AICs, perform detailed residual analysis for each. The model whose residuals best approximate white noise, e.g., through Ljungbox test results, might be the better choice. For this example, let's assume code snippet is identified as the best model or is chosen due to its balance of fit and parsimony among similarly performing models. Ving the model selection results. For reproducibility and future reference, it's often useful to save the code snippet containing the AIC values. Download the code on one PACF Substack. 5. Fitting the optimal model. With code snippet identified as our optimal model, we now fit it to the entire training dataset. We use code snippet from code snippet as it's a versatile implementation that can handle ARMA models by setting code snippet for the differencing order, as our data is already differenced. A crucial detail here is code snippet within the code snippet model. Since we have manually differenced our code snippet to ensure stationarity, we explicitly tell code snippet not to apply any additional internal differencing. If we had passed the original non-stationary data and specified code snippet in the code snippet tuple, code snippet would handle the differencing itself. By setting code snippet and providing pre-difference data, we maintain full control over the differencing process. Download the code on one PACF Substack. The model summary provides detailed statistics about the fitted model, including coefficients, standard errors, p-values, and overall model fit statistics like AIC, BC, and HQIC. This summary is a rich source of information for advanced model evaluation, but for now, our focus is on validating the model's residuals. 6. Comprehensive residual analysis. The final and most critical step in validating an ARMA model is to analyze its residuals. For a model to be considered well-fitted and suitable for forecasting, its residuals must resemble white noise. White noise means the residuals are 1. Uncorrelated, no remaining patterns or information that the model failed to capture. 2. Zero mean, the errors average out to 0. 3. Constant variance, the spread of errors is consistent over time. Homoscedasticity. 4. Normally distributed. While not strictly required for model fitting, normality is an assumption for many statistical tests and confidence intervals. We assess these properties both qualitatively, using diagnostic plots, and quantitatively, using statistical tests. 6.1 Diagnostic plots for residuals. Code snippet provides a convenient code snippet method that generates 4 key plots. 1. Standardized residuals. Plots the residuals over time. We look for no discernible patterns, constant variance, and residuals centered around 0. Any trends, increasing/decreasing variance, or obvious cycles indicate issues. 2. Histogram plus estimated KD shows the distribution of residuals compared to a normal distribution. We look for a bell-shaped curve centered at 0. 3. Normal QQ plot compares the quantiles of the residuals to the quantiles of a theoretical normal distribution. If the residuals are normally distributed, the points should fall closely along the 45-degree line. Deviations, especially at the tails, suggest non-normality. 4. Correlogram. ACF plot of residuals displays the autocorrelation of residuals at different lags. For white noise, all autocorrelation coefficients, except at lag 0, should fall within the confidence intervals, the blue-shaded region, meaning they are not statistically significant from 0. Download the code on one PACF Substack. Interpretation of diagnostic plots. Standardized residuals plot. We observe that the residuals fluctuate around 0 with no apparent trend or changing variance. This is a good sign, indicating the model has captured the underlying patterns. Histogram plus estimated KD. The histogram shows a distribution that is roughly bell-shaped and centered around 0, aligning well with a normal distribution. Normal QQ plot. Most of the points lie very close to the 45-degree line, especially in the middle. Some minor deviations at the tails are common in real-world data, but do not significantly undermine the model, if the other checks pass. A bad QQ plot would show points significantly curving away from the line, especially if they form an S-shape or a distinct curve, indicating skewness or heavy tails. Parallelogram, PACF plot. This is perhaps the most crucial plot for time series residuals. For our code snippet model, nearly all autocorrelation spikes are within the blue shaded confidence intervals, indicating that the residuals are uncorrelated. This confirms that our model has effectively captured the serial dependence in the data, leaving only white noise. A bad parallelogram would show several significant spikes, extending beyond the blue region at various lags, implying that there is still autocorrelated information in the residuals that the model failed to capture. 6.2 Ljung box test for residual autocorrelation. While the parallelogram provides a visual assessment, the Ljung box test offers a formal statistical test for the presence of autocorrelation in the residuals. Null hypothesis. H0 the residuals are independently distributed, i.e., they are white noise. Alternative hypothesis. H1 the residuals are not independently distributed, i.e., there is significant autocorrelation. We want to fail to reject the null hypothesis, meaning we want high p-values, typically greater than 0.05 for all tested lags. Download the code on one PACF Substack. The Ljung box test results, specifically the code snippet column, confirm the visual assessment from the parallelogram. If all p-values are greater than 0.05, we fail to reject the null hypothesis, concluding that there is no significant autocorrelation in the residuals. This is the desired outcome, indicating a well-fitted model. What if residual analysis fails? If the residual analysis indicates that the residuals are not white noise, e.g., significant spikes in the parallelogram, low Ljung box p-values, or patterns in the standardized residuals plot, it means our current model has not fully captured the underlying structure of the time series. In such a scenario, you would need to 1. Reevaluate differencing. Could more differencing be needed, e.g., second-order differencing or seasonal differencing? Check the ADF test again. 2. Expand code snippet and code snippet ranges. The optimal code snippet might be outside the initially chosen search range. Try a wider range for code snippet and code snippet. 3. Consider higher-order models. If simple ARMA, PQ is insufficient, perhaps the series exhibits seasonality that requires a seasonal ARMA, SARMA, or seasonal ARMA, SARIMA model. This involves adding code snippet components to the model order. 4. Examine ACF/PCF of residuals. If the Ljung box test fails, look closely at the parallelogram of the residuals. Significant spikes at specific lags might indicate the exact code snippet or code snippet terms that are still missing from your model. For instance, a significant spike at lag 7 might suggest adding in code snippet term or code snippet. This iterative process of modeling, fitting, and validating is fundamental to robust time series analysis. 7. Brief look at forecasting. While detailed forecasting is covered in subsequent sections, it's useful to briefly demonstrate how to generate forecasts using our fitted model. This provides an immediate practical outcome of our modeling efforts. We'll generate forecasts for the next few hours, e.g., the first 2 hours of our test set. Remember that these are forecasts of the different series. To get forecasts of the original series, we would need to reverse the differencing transformation, a proc. S called inverse differencing or integration, which is covered in detail later. Download the code on one PACF Substack. This snippet shows the predicted values for the different series. In a real-world application, these forecasts would then be inverse transformed to provide predictions for the actual bandwidth usage, which is the ultimate goal. This comprehensive application demonstrates the full life cycle of ARMA model development, from raw data to a validated model. This general procedure is highly applicable across various domains, including financial data, e.g., stock prices, trading volumes, energy consumption, sales figures, and healthcare metrics, whenever you need to understand and predict time-dependent phenomena. Error. Gemini API failed to generate content after 3 attempts. Summary. Consolidating ARMA modeling principles. This section serves as a comprehensive recap, reinforcing the core concepts of autoregressive moving average, ARMA, models, the systematic general time series modeling procedure, and the critical limitations of traditional tools like ACF and PACF plots when identifying ARMA process orders. We will also revisit the indispensable role of the ACICA information criterion, AIC, for model selection and the rigorous process of residual analysis for model validation. The Autoregressive Moving Average, ARMA, model revisited. At the heart of many stationary time series analyses lies the Autoregressive Moving Average, ARMA, model. This powerful framework combines two fundamental components. Autoregressive, AR, component, denoted AR-P. This part models the current value of the series as a linear combination of its own past code snippet values. It captures the dependence of an observation on its preceding observations. Moving average, MA, component, denoted MA-Q. This part models the current value as a linear combination of past code snippet error, or white noise, terms. It captures the impact of past random shocks on the current observation. When combined, an ARMA-P Q model describes a stationary time series $YT as a function of its past values, $YTI, and past error terms, $\epsilon. Recall its general mathematical form, which synthesizes the autoregressive and moving average parts. $YT equals C plus backslash phi 1 YT, 1 plus backslash dots plus backslash P. Hip YTP plus backslash epsilon plus backslash theta 1 backslash epsilon 1 plus backslash dots plus backslash thetac backslash epsilon TQ$, where $YT is the value of the time series at time $T$. $C$ is a constant. $phi are the autoregressive coefficients. $epsilon is the white noise error term at time $T$. $theta are the moving average coefficients. $P$ is the order of the AR part. $Q$ is the order of the MA part. In Python, the code snippet library is the primary tool for implementing ARMA models. The code snippet class, which handles ARMA, ARMA, and Ceramax, provides a robust framework for estimation. Download the code on one PageCode Substack. This initial step demonstrates how you would conceptually load your time series data and prepare to define an ARMA model using code snippet. The code snippet tuple code snippet is crucial, where code snippet for a pure ARMA model, as opposed to ARMA, which includes differencing. Why ACF and PACF plots fall short for ARMA order identification. While autocorrelation function, ACF, and partial autocorrelation function, PACF, plots are invaluable for identifying the orders of pure AR, P, or pure MA, Q. Processes, their utility diminishes significantly when dealing with mixed ARMA, P, Q models. For pure AR, P, processes, the ACF typically decays exponentially or sinusoidally, while the PACF cuts off sharply after lag code snippet. For pure MA, Q, processes, the ACF cuts off sharply after lag code snippet, while the PACF typically decays exponentially or sinusoidally. However, for an ARMA, P, Q process, both the ACF and PACF plots generally exhibit a complex pattern of exponential decay or sinusoidal behavior, rather than clean cutoffs. This makes it challenging, if not impossible, to visually determine the specific code snippet and code snippet orders directly from these plots. The fingerprints of AR and MA components become intertwined and obscure each other. This limitation necessitates a more systematic approach to model identification, leading us to the general time series modeling procedure. The general time series modeling procedure. Given the complexities of identifying ARMA orders from ACF/PACF plots, a robust, iterative procedure is essential. This general modeling procedure typically involves the following steps. 1. Model identification. Initial guess based on theoretical understanding, preliminary ACF/PACF analysis, looking for general patterns, not sharp cutoffs, and prior experience, propose a range of plausible ARMA, PQ candidate models. This is often an iterative process where you test different combinations of code snippet and code snippet. 2. Parameter estimation. For each candidate model, estimate the model parameters $\phi$, $\theta$, and $C$, using maximum likelihood estimation, MLE. 3. Model selection. Compare the fitted candidate models using information criteria, primarily the ARMA information criterion, AIC. The goal is to find the model that provides the best balance between goodness of fit and model complexity. 4. Model validation. Residual analysis. Critically assess the residuals of the chosen model. Ideal residuals should resemble white noise, indicating that the model has captured all the systematic information in the data. If residuals are not white noise, the model is inadequate, and you must return to step 1. This iterative loop of identification, estimation, selection, and validation is crucial for arriving at a parsimonious and accurate model. Model selection with ARMA information criterion, AIC. The ARMA information criterion, AIC, is a cornerstone of model selection. Its primary purpose is to help choose the best model among a set of candidate models. AIC balances two competing desires: goodness of fit, how well the model explains the observed data; model complexity, the number of parameters used by the model. A more complex model, more parameters, will generally fit the training data better, but it risks overfitting and performing poorly on new, unseen data. AIC penalizes models for having more parameters. The formula for AIC is $AIC equals 2K, 2\ln L$, where $K$ is the number of parameters in the model. $L$ is the maximum likelihood value for the model. Interpretation. When comparing multiple models, the model with the lowest AIC value is generally preferred. A lower AIC suggests a model that provides a good fit to the data without being overly complex. Important considerations. Relative measure. AIC is a relative measure. It only tells you which model is best among the ones you've tested. It doesn't tell you if any of your models are good in an absolute sense. Stationarity. AIC is typically used for models fitted to stationary data. Applying it to non-stationary data can lead to misleading results. Data size. For very large data sets, the penalty for complexity might become less significant, potentially leading to selection of overly complex models. In code snippet, the AIC value is automatically calculated and available after fitting an ARMA model. Download the code on OnePageCode Substack. By comparing code snippet and code snippet, you would select the model with a lower AIC. This process is typically automated by iterating through a grid of possible code snippet values. Residual analysis, the ultimate model validator. After selecting a model using AIC, the most critical step is to validate its adequacy by analyzing its residuals. Residuals are the differences between the observed values and the values predicted by the model. For a model to be considered valid and to have captured all the systematic information in the time series, its residuals must resemble white noise. Characteristics of ideal white noise residuals. 1. Uncorrelated. There should be no discernible pattern or autocorrelation in the residuals. Each residual should be independent of past residuals. This is the most crucial characteristic for time series models, as any remaining correlation implies that the model hasn't fully captured the underlying time dependence. 2. Normally distributed. The residuals should ideally follow a normal distribution with a mean of 0. This assumption is important for the validity of statistical inference, e.g., confidence intervals for forecasts. 3. Constant variance. Homoscedasticity, the variance of the residuals, should be constant across time. Heteroscedasticity, non-constant variance, suggests that the model's predictive power varies over time. We use both qualitative and quantitative methods to assess these characteristics. Qualitative assessment, the QQ plot for normality. The quantile QQ Plot is a graphical tool used to qualitatively assess whether a dataset, in this case residuals, follows a specific theoretical distribution, typically the normal distribution. Purpose: to visually check if the residuals are normally distributed. Interpretation: if the residuals are approximately normally distributed, the points on the QQ plot will lie close to a straight line. Deviations from the line, especially at the tails, indicate departures from normality, e.g., skewness or heavy tails. The code snippet function is used to generate QQ plots. Download the code on OnePageCode Substack. This code snippet generates a QQ plot for your model's residuals. You would visually inspect this plot to ensure the points align closely with the 45-degree line, confirming approximate normality. Quantitative assessment: the Ljungbox test for autocorrelation. While visual inspection is helpful, a quantitative test provides statistical evidence. The Ljungbox test is used to formally check for the absence of autocorrelation in the residuals. Purpose: to quantitatively assess whether the residuals are uncorrelated, i.e., whether they constitute white noise. Hypotheses: null hypothesis, $H0 the residuals are independently distributed, i.e., there is no autocorrelation up to a specified lag. Alternative hypothesis, $H1 the residuals are not independently distributed, i.e., there is significant autocorrelation at one or more lags. Interpretation: the test calculates a p-value. If the p-value is greater than your chosen significance level, e.g., 0.05, you fail to reject the null hypothesis. This is the desired outcome, as it suggests that there is no significant autocorrelation in the residuals, and they can be considered white noise. If the p-value is less than or equal to the significance level, you reject the null hypothesis. This indicates that there is significant autocorrelation in the residuals, meaning your model has not adequately captured all the time dependence in the data, and further model refinement is needed. The code snippet function performs this test. Download the code on OnePageCode Substack. The output of this code will show the Ljungbox statistic and the p-value for each specified lag. You should inspect the code snippet column. If all p-values are above your significance level, e.g., 0.05, your resi duals are likely white noise. What if residuals are not white noise? If residual analysis reveals that your model's residuals are not white noise, e.g., QQ plot shows strong deviations, while Ljungbox p-values are consistently below 0.05, it means your model is inadequate. This indicates that there is still systematic information or patterns in the data that your model has failed to capture. In such cases, you must return to the model identification step 1 of the general procedure, and consider trying different code snippet and code snippet orders. Perhaps a higher order ARMA model is needed. Considering seasonality. If the time series exhibits seasonal patterns, an ARMA model might be insufficient, and a seasonal ARMA model might be more appropriate. Checking for structural breaks or outliers. Unusual events can distort residuals. Re-evaluating stationarity. Ensure the original series was properly differenced if it was non-stationary. The iterative nature of time series modeling means that residual analysis is not just a final check, but a crucial feedback mechanism that guides further model refinement.